In this video, we are going to cover everything about IMAT chemistry. In the next few hours, Joanne, who is also another fellow medical student, is going to teach students everything about IMAT chemistry portion and also going to solve past year questions which were asked in the actual IMAT exam. With that regard, I would like to invite Joanne for her introduction.
Hello, everyone. I'm Joanne, a medical student, and I'm really excited to help you tackle the chemistry section of the IMAT. We created this one shot course with a simple goal to make chemistry easier to understand, less intimidating, and ultimately help you maximize your score on the exam day. Many students treat chemistry as a subject where you have to memorize everything, but in reality, it's one of the most logical sections of the IMAT. Once you understand the patterns behind why elements behave the way they do, chemistry starts making sense, and you stop guessing answers and start solving them with confidence.
Exactly. So that is the spirit when we are actually studying chemistry. And with that regard, I would also like you to deliver an advice to the students on how they are going to stick with you for the next few hours and how they should approach and they should look over the chemistry portion for the IMAT exam.
Okay, so don't overlook the fundamentals. Topics like moles and stoichiometry may seem basic, but a huge number of marks are lost, not because the chemistry itself is difficult, but because the calculations aren't done carefully. The students who score the highest aren't always the ones who read the most. They're the ones who practice the most, make mistakes, learn from them, and keep going. So let's turn chemistry from your biggest fear into your easiest marks. Because every question you truly understand today is one question you'll have to worry less about on the exam day.
Exactly. So that was a very wonderful advice from your side. And all the best to all the students who are going to follow you throughout the one shot video. And I'm really grateful for Joanne for helping the students who will be giving IMAT in the future. Thank you so much. And I wish everyone the best throughout the video. And I hope you learned something of chemistry. And I hope this video will be helpful to you. Thank you.
Hello, dear future doctors. I hope you are doing well, watching from different parts of the world, from different time zones. And I really hope your IMAT preparation is going well too. So, I'm here today with a one shot video for your chemistry portion of your IMAT syllabus. And this video will contain, or this lecture contains the entire IMAT syllabus in a gist, right? In a gist with some tips and tricks and the IMAT PYQs over the past 5 years, or in a few, a little more than that, right? Yes, a little more than that, and that's that. So, without any further ado, let's get started. Please grab a book, a pen, and let's crack IMAT chemistry together, one molecule at a time. All right? Yes. So let's start with a question that lies at the heart of chemistry. How are chemists possibly able to count molecules or particles that are impossible to see? And the answer is mole concept, right? So, what's mole concept? I would personally say mole concept is chemistry's way of calculating a dozen, right? So, one mole is equal to Avogadro number of particles. An Avogadro number is this, something that we've been always learning. You should also remember that one mole is a counting unit and it is not a mass unit, right? And it can be applied to atoms, molecules, ions, electrons, and protons. Now, what are the fundamental particles? We know we have electron, proton, and neutron. Electron and proton are identical in charge but different in magnitude. Okay? And in the same way, proton and neutron have the same mass. Okay? And then we have atomic mass. Atomic mass can be explained as you weigh how heavy an atom is with respect to a standard atom. And normally we consider hydrogen to be the standard atom, right? AMU is atomic mass unit. And then we have molecular mass. You cannot possibly perform any questions, any calculations without knowing the molecular mass. the sum of the atomic mass in a molecule is nothing but the molecular mass, right? Now we have the average atomic mass. This is of great importance because when you see isotopes, you always, for example, hydrogen, it has 3 isotopes. The value that you see on the periodic table is nothing but the weighted average of the isotopes, right? So it depends on the percentage abundance. The next 4 concepts, that is gram atomic mass, gram molecular mass, formula mass, and molar mass, they are the same concepts, just in a different form, or I would say like a way that is said, right? So gram atomic mass is nothing but the atomic mass expressed in grams. It contains Avogadro number of atoms. Gram molecular mass expressed in grams, contains Avogadro number of molecules. Formula mass, it is used for ionic compounds. By far, I haven't seen any kind of questions based on formula mass. I don't know, maybe you could possibly expect some kind of questions from this. And then we have molar mass, again, very important. Mass of 1 mole of substance, and the unit is gram per mole. And then we have vapor density. It is of great importance when it comes to empirical formula and the molecular formula that we're going to see, because Vd gives you the molecular mass divided by 2. Percentage composition, percentage of element is equal to molecular mass divided by the mass of element into 100 percentage, right? And then you have mole calculations. Basic formulas: particles is nothing but moles into Avogadro number, mass is nothing but moles into molar mass, and N, which is nothing but the number of moles, is the given mass in grams divided by the molar mass. And you have the molar volume. 1 mole of gas at STP, standard temperature pressure, is equal to 22.4 liter. If this is not mentioned in the question, if it is not mentioned either as just the word STP, or if it's not mentioned, they would either give you the temperature as 273 Kelvin or the pressure as 1 atm. If it is not mentioned, it is not, you cannot use this value in the question. All right. And then you have the empirical formula. Empirical formula and the molecular formula are 2 things that are correlated. Why? Because empirical formula is more like the base or the skeleton, and molecular formula builds on the empirical formula. If you look at this example, this is not something that you see in chemistry, right? In real life chemistry, you do not see this in your organic chemistry, because it is the simplest ratio of atoms. It just gives you the ratio. You will use this to build the molecular formula, which is the actual number of atoms, right? You will multiply the subscript by n, which you will get by dividing molecular mass divided by empirical mass. And now you have the most important formulas or the concepts of this chapter, the dilution formula. M1V1 is equal to M2V2, right? And then you have stoichiometry. What is stoichiometry? Anything to deal with coefficients has to be stoichiometry, right? And then you have limiting reagent. Reactant that gets consumed first determines product formed, okay? Found by comparing mole ratios. Now, one important concept that I should mention is that you will have questions based both on stoichiometry and limiting reagent. It's important you know how to classify which question has to follow the stoichiometry rules and which one has to follow the limiting reagent. Which one is the limiting reagent? I personally found it really hard when I was preparing for the IMAT. So what I did is, one reactant in a question, if there's just one reactant values or any data that's given only for one reactant, it is usually stoichiometry, okay? But if there are two reactants, it can be anything, number of moles or even volume, and because they will always give you either the volume, all of that would be given, and find the number of moles. It would be twisted, but you just need to make sure, get the moles. You get the moles and you can solve any kind of questions. Having said that, one reactant is usually stoichiometry. Two reactants, you can suspect a limiting reagent, right? And how do you get which one is the limiting reagent? Firstly, what do is you find the number of moles. All right. Once you find the number of moles, as I said, the second step is coefficient. What is the coefficient? The value that lies below the reactant or the product. It's normally the reactant that you take in a picture for the limiting reagent, and you divide it by the number of moles. Number of moles divided by the coefficient. Sorry. Yeah, and the smaller value becomes the limiting reagent. I hope that's clear. Now you have the concentration terms. When you see temperature dependent, everything that has to strike your mind is volume, right? Anything at all that has volume in its denominator is temperature dependent, right? Here you can see the entire thing has volume. You have volume here. Molarity, volume, right? So everything that does not have volume in its formula is temperature independent. As simple as that. No volume. Mole fraction does not have volume. Molality has mass instead, so no volume. Parts per million, no volume. No volume in the picture at all. Yes, this is a quick memory tip. And now we move on to the PYQs. Alright, so how many ml of water must be added to 15 ml of 0.25 m solution of H2SO4 to obtain a 0.05 m solution? Before I start solving, I would highly recommend you pause the video here. Just try and look at the question, cover the answer, and try to solve it by yourself. Alright? Yes. So this is water must be added. Dilution. Dilution question. As soon as you see that, right? You remember M1 V1 is equal to M2 V2. In dilution, the amount of solute never changes. Please remember that, right? Dilution increases the volume. Okay, so because the volume increases, the concentration decreases, right? Volume increases, concentration decreases, but the number of moles, the amount, remains the same. Okay, this is remains the same. This is something that you need to keep in mind. Okay, so you just apply it here, you get V2. This is just V2, but they're asking the amount of ml of water that must be added to 15 ml. You're adding something, so you definitely have to subtract, right? And when you subtract, you will get B to be the answer. Next question. How many Na plus ion moles can be found in 250 ml of a 1.2 m solution of Na2S2O4? Okay, so whenever ions appear in the question, inspect the subscripts. What is the subscript? These, right? This 2, 2, 4. Those are the subscripts before any calculation. All right, 1.2 into 0.25, you're converting into liters, is equal to 0.3 moles. You're just using the molarity formula and you get 0.3 moles. That's the total number of moles. But each mole gives 2 Na plus moles. You're finding that respective one, right? So you multiply it into 0.3 and you will get 0.6, as they are particularly asking how many Na plus ion moles, and this one is the total moles. So please be careful. And so you get B to be the answer. Okay, I hope it's going well so far. Let's move on to the third question. Given that the relative atomic mass of nitrogen is 14 U, how many nitrogen atoms, please, atoms, are present in 0.7 grams of gaseous nitrogen? Firstly, important to know, gaseous nitrogen is N2, right? And they're asking, what is N2? N2 is a molecule. But they're asking atoms. N plus N gives you N2. So this N is an atom and N2 is a molecule. So please be careful, right? So molar mass of N2, 14 into 2, so 28 moles you find. You get 0.025 moles. And then you find the molecules. Molecules, if you remember in the first slide, you just multiply it into the Avogadro number and you get this to be your answer. And it does match. So C is your answer. So please remember, this is a quick trick. Mass, convert it into moles, moles into molecules, molecules into atoms. Okay, it's very important you learn to differentiate between molecules and atoms, because you could have possibly gone wrong if you just took 14, right? And thought gaseous nitrogen is just like N. So please be careful here. And always remember, please convert into moles. You will somehow land in your answer, or close to your answer at least. Okay? And then we have the fourth question. Carbon and oxygen can react at high temperature to form CO2. Assuming that the relative atomic mass of carbon is 12U, the relative atomic mass of oxygen is 16U, and the yield of the reaction is 100%. What happens when 9 grams of carbon reacts with 36 grams of oxygen? Okay. Okay, let's start. Firstly, write the equation. Okay, so moles again, remember. Anywhere, anytime moles. You find the number of moles for both, right? You got both. And you can see it is in 1:1 ratio. And one more important thing, the values of 2 are given, right? Of 2 are given. If you remember the trick that I gave you in the limiting reagent slide, is that when the values of 2, any value, but if both of the reactant values are given, remember limiting reagent. So we use the same concept here, and you can see it is in 1:1 ratio. And so you don't have to worry about the coefficient. Whatever is limiting in this becomes a limiting reagent. So here you can see that 0.75 is the limiting reagent. So O2 left will be, you are going to subtract. But you can see that there's no answer that's matching. And so you need to go a step higher and solve for mass of CO2, because that is possibly the only thing that can be seen in the question, right? So in case if you get stuck, because because I went through this, you do until here, and then you look at the answers and you do not find anything that's matching. Please make sure you move on to the next step and try to solve higher. So always go solve your questions based on the options that you have. It makes life a lot easier, right? And so you solve for mass of CO2 and you get 33 grams, and that matches E. Okay, and then we have the fifth question. What is the minimum mass of sulfur dioxide needed to make 500 ml of a solution of concentration 3 mole per liter? Direct. Molarity is equal to N by V. You find the number of moles, molecular mass of SO2, you find, and then you find the mass, you get 96 grams. Very easy question, right? So this is your quick conversion map. Mass to moles or particles to moles, either way, and then you get volume, and then you get concentration. Always and always moles. Okay? Yes. Let us now move on to the next chapter, that is solutions. Okay? Solutions is more about formulas. That's it, right? And you just have to have a little bit of understanding here and there, but again, it's important. Okay? Yes. Solution is nothing but a solute with a solvent. Simple. And the solute is always and always in the lesser amount, and the solvent is always in the greater amount. One important thing is that water is not always a solvent, right? You should always remember the one in the greater amount becomes the solvent, and the one in the lesser amount becomes the solute. Okay? And then you have the percentage concentration terms, V by V, W by V, W by W. V by B is liquid in liquid. One example is your perfumes that we use. It uses this particular concentration term. And then you have solid in liquid, right? The saline in drips uses this one. And then you have solid in solid or mass basis, so W by W, right? And then you have molarity again. So M is equal to N by V, number of moles divided by volume in liters or ml. Then you have molality. The only difference here is you use weight of solvent in kg, but here it's volume, right? This is not of great importance, but it's good to know. So yes, molal is nothing but M, semi-molal M by 2, a deci, so divided by 10, right? And then you have mole fraction. So what fraction of all particles belong to a particular component. Okay, so it's again the number of moles is what, by the term itself, is what you basically count this formula on, right? And the mole fraction of A and the mole fraction of B, when you add, is always and always equal to 1. Okay, this can come handy in some of the questions. And then you have vapor pressure. Let me give you an example. This water bottle, which has water inside it, the water inside is always trying to evaporate into a gaseous phase. Okay, so basically the liquid is trying to overcome the pressure to evaporate into gaseous phase, right? So the rate of evaporation is equal to the rate of condensation. And then you have Raoult's law. Raoult's law is rather based more on the pressure and mole fraction. So you can say it is directly proportional, right? So what happens is that there are two kinds of cases. One is non-volatile solute with a volatile solvent, and volatile solute plus the volatile solvent. These are the important formulas that you should know. If there's a non-volatile solute, right? Always remember the vapor pressure decreases. Okay? And then you have types of solutions. You have ideal solution. It's only possible in theory. In real life, never. Okay, because it follows the Raoult's law. Okay, and so A A to A, B to B, and A to B is all equal. So heat is neither absorbed nor released, and so delta H, that is enthalpy, is zero, and delta V again is zero. Example: hexane and heptane, hydrocarbons, right? And then you have your non-ideal solution. You have negative deviation, positive deviation. In negative deviation, there is stronger attraction, so it is harder to escape, and so there is lower vapor pressure, right? And so delta H is lesser than zero. So chloroform and acetone, acid and water, these can be the examples for negative deviation. And for positive deviation, weaker attraction, and so higher vapor pressure. And so delta H is greater than zero. The examples are again here. Okay. And then you have the most important concepts of this chapter: colligative properties. Colligative properties is something that depends entirely on the number of particles and not on anything else, right? So the relative lowering of vapor pressure, elevation of boiling point, depression of freezing point, and the osmotic pressure. So firstly, the relative lowering of vapor pressure. You have this formula. So more particles lower the vapor pressure, right? And then you have elevation in boiling point. This reminds me of the classic example. When we are making pasta, you add salt to the pasta while you are boiling it. And why is that? Of course, for flavor, but more importantly, to increase the boiling point. And so it gets evenly boiled and the boiling increases. And so that's the reason. So particles increases, boiling point increases, right? This is molality, right? Not molarity, molality. So depression in freezing point, again, particles increases, freezing point decreases. And then you have the Van 't Hoff factor. I is nothing but the particles after dissociation or the particles before dissociation. Example: urea, glucose, sucrose, they are all non-electrolytes, and so the I is equal to 1. But for electrolyte, I'm giving an example here: NaCl, CaCl2, where when you have to find I for any, if they give you a molecular formula and ask you to find I for that, you will always try to get the dissociation equation. And this can be the dissociation equation for any formula. Just try to break it down and put their subscripts in their coefficients. And you will be able, this is N, and you will be able to find I using this N. So dissociation when I is greater than 1, and association when I is less than 1. Okay. Osmotic pressure, pi is equal to ICRT, right? You have solvent moves through the semi-permeable membrane from lower concentration to the higher concentration. Okay. Yes. Next, you have tonicity. Isotonic equal hypo, hypo, so less osmotic pressure, hyper, so more osmotic pressure. And then you have solubility. Solid in liquid depends on temperature. Endothermic, so it increases the solubility. Very important. Exothermic, it decreases the solubility. Pressure has no effect. This is extremely, extremely important, right? And then you have gas in liquid. Classic example. Why are carbonated drinks more carbonated when they are in the fridge or when they are cooled rather than when you keep it outside? Temperature, right? Always exothermic. It increases temperature, therefore the solubility decreases. Pressure increases pressure, solubility increases. Henry's law. Classic example again about the sea divers. P is equal to KHX, right? This is the Henry's law constant, right? And then you have the important terms that we've already done. Let's move on to the PYQs. How much water needs to be added to 1 ml of an HCl solution with a pH of 2 to obtain a solution with a pH of 4? There are two methods to solve this. There can be even more. I'm not saying that you should follow this, but please know that you should just get the concept right and you're good to go. So, the method one that I used, I got the pH of both, converted it into getting the concentration, which you know pH is equal to log concentration. Um, yep. And then because you got the concentration, and when you can see that 10 to the power minus 2, 10 to the power minus 4, 100 times smaller. And if you remember from the first lecture, I also mentioned that concentration and V, if concentration increases, V decreases. Same concept. V is because concentration is 100 times smaller, this is 100 times larger. And so V1 is 1 ml, V2 is 100 ml, H2O added is 100 minus 1, you get 99. Whenever they say H2O added, please remember in the last step you will have to subtract. You will have to subtract the volumes, right? Method 2, the classic dilution example, method, you use the same thing, V2, H2O added, so don't forget to subtract. And you have 99 ml, which is A. The next question. A pH meter is used to test 0.1 mole per liter aqueous solution of the following compounds. Acetic acid, NaCl, H2SO4, BaOH twice, HNO3. Which of the following correctly lists the solution in order of increasing pH? This is with relation to your acids and bases or your ionic equilibrium. But it's important you know that you have no formula to solve this, right? And it should strike your mind when you are solving these kind of questions. So they're asking in order of the increasing pH, right? So CH3COH, acetic acid, we all know it's a weak acid. So higher pH, but below 7, right? And NaCl, if you know hydrolysis, from a strong acid, we have HCl. From a strong base, NaOH. And so both are in 1:1 ratio because there's no subscripts. And so it is neutral. So the Na in the NaCl, you have it from here. And the Cl from in the NaCl, you have it from HCl. You will learn it again in ionic equilibrium. And then you have H2SO4, strong acid, so the least pH, BaOH twice, strong base, so the higher pH, but again, yes. And then you have HNO3, strong acid, yes. But the only catch here is you need to differentiate which is the stronger acid here because it's all the others are easy, like you have a direct answer in your mind. But remember, H2SO4 is always and always a stronger acid, so it will have a lower pH compared to any other acid, right? And the options match 3, 3 and 5. Yep. So you have A to be your answer. Yep. Yes. And then you have the third question, a more theoretical question. So sucrose is added to water until no more dissolves. So saturation. Which statements are correct? A saturated solution is produced, definitely. It mentions here indirectly. Freezing point is equal to 0 degrees. No, adding solute lowers the freezing point. It's a colligative property. Sucrose is non-polar. No, sucrose chemical formula is this, right? So it has OH groups. So definitely not non-polar. It is polar. Sucrose is the solute. Yes. So you have 1, 2, and 4 to be the answer. So you have E to match the option. Yes. And then you have the fourth question. Fourth question again comes from your acids and bases. A few drops of universal indicator solution were added to exactly 50 ml of NaOH solution. Exactly 50 ml of HCl of concentration so much was added drop by drop to the sodium hydroxide solution containing the universal indicator solution. So, what color changes would be observed as the HCl was added, right? Unfortunately, for this, you will need your the pH scale. The colors, you should know the colors in the scale. So, yes, I've attached it here so it's easy for you. Maybe you can just understand it and get a clear picture of that. But yes, the start state is NaOH, strong base. The color, violet, strong base, violet, right? As HCl is added, the pH decreases, obviously, because HCl is a strong acid. And so from base, it goes to neutral, right? So equal moles react, final solution, neutral stops at green, right? So this is an example of the one that we did here. Like here we try to find the hydrolysis, right? HCl NaOH, the same way because we mentioned here, it's neutral. So please do not go more than 7, you stop at 7, right? Violet, blue, green, violet, blue, and green. It stops here because it's on hydrolysis. You get a neutral compound or neutral salt, and so this is your option. I hope you understood this. This was a nice question. Yes. And next we have which one of the following substances has the highest solubility in the specified liquid at a temperature of 298 Kelvin and 1 atm pressure? This is STP, right? Just telling you. But yes, so we know that like dissolves like. Polar dissolves polar. And the non-polar dissolves non-polar. And so you can see here NaCl and cyclohexane. The solute here, NaCl, is polar, whereas solvent non-polar and so poor. So not possible. Br2 and hexane. Solute is non-polar, non-polar. So excellent. And so you have 2. But still, let's move on to the other 3. It's important for theory questions. Please make sure you go through every question. You will form your own questions when you are going through every option in the question for theory only, right? So H2 and water, non-polar solute H2 and polar, so not possible. KBr and CCl4, polar and non-polar, not possible. SiO2 and water, covalent, giant covalent and polar, poor, not possible, right? So, yep, that's that. And yes, all right. So now let's move on to the next chapter or next unit, that is the structure of atom, right? It's not a very difficult chapter. You just need to understand the basics. But we have gone a little more in depth. It's just for understanding and just to broaden your knowledge about this chapter, right? So let's start. Fundamental particles, as we already did, electron, proton, and neutron, their mass, charge, their relative mass, relative charge. And then you have the discovery of electron. The cathode rays are the fast moving electrons, right? So cathode rays are basically electrons, right? Basically electrons. So because electron is negatively charged, negative charge always moves to the positive side, and so cathode always moves to anode, right? So it's negative and positive. So which particle contributes most to the atomic mass? Protons and neutrons, and not electrons. Atomic mass. Because electrons lie on the orbit, right? They are here. And you have protons and neutrons to be at the center. So cathode rays consists of negatively charged particles called electrons, as I mentioned. They travel in straight line. Cathode ray possesses mass, energy, penetration power. When electric field is applied, they are deflected towards the positive side of the field. As I told you earlier, they produce X-rays when they strike heavy nucleus like tungsten or molybdenum. Specific charge or charge by mass or ionic potential of all cathode rays are same irrespective of the gas present inside the discharge tube. Very important for a theoretical aspect. Yes, so the mass of the electron and the charge of the electron. Magnitude minus. Anode ray. Anode ray is fast moving, positively charged ion. The direction, because it's positive, it moves to negative, right? And so it's positively charged ion, travel in straight line. They possess mass, energy, penetration power, just like electron. When electric field is applied, they are deflected toward the negative side of the field, like electron. Specific charge or charge by mass ratio or ionic potential is not the same. It depends on gas inside discharge tube. This is the contrasting what you did here, right? Um, is same. It's the same sentence, but here it's is same. Here it is not the same. And so, what varies in anode ray? Gas. It depends on the gas, which wasn't the case in cathode ray. So, in case of hydrogen, anode ray are termed as protons, like we know. This is just a comparison table that can help you understand this. Everything that IMAT wants to know about neutron is that James Chadwick discovered neutron, right? And now the most important part of the chapter, representation of element. Mass number A, number of protons plus number of neutrons. Atomic number is nothing but the number of protons. Number of neutrons is your mass number minus the atomic number, right? Direct formulas. Yes, these are the notes, units for of energy, units of length, distance, and these are important for your conversions. If they are not mentioned, it's important for you to know these values for conversion, right? This is angstrom, this is a nanometer, and angstrom. Okay. Yes. And then you have the iso series. Isotopes, like we know, same atomic number but different mass number. Hydrogen, right? Isobars, I used to remember this as because it's isobars, so same weight bar, and so same mass number, weight. So, yeah, and different atomic number. And isotones, here you have ons, ONES. So you have ons, neutrons. So same number of neutrons is isotones. Isoelectronic, same number of electron in the word itself, right? Isodiaphers, having same isotopic number, right? And isosters, molecules having same number of atoms and same number of electrons. Next, we have the atomic model, the J.J. Thomson model, the plum pudding or the watermelon model, where the positive charge is all around the atom and the electrons are embedded in between. The classic example, right? Next, you have the Rutherford alpha particle scattering experiment. Because Thomson couldn't explain this and it was a drawback, you have Rutherford to explain this. So, what did he say? Most of the alpha particles went straight. Few alpha particles were deflected by small angles. Very few alpha particles, 1 in 20,000, deflected by 180 degree. So the conclusion was most of the space inside atom is empty. So positive charge is present at the center of atom called nucleus. And then you have proton plus neutron, nucleons, right? So the radius of atom is 10 to the power of minus 10 meter. The radius of nucleus is 10 to the power of minus 15 meter. Yes, and this is an important uh, thing to remember. It can come as an MCQ, just a theory, you know. Yes, the limitations were it could not explain the internal distribution of electrons and could not explain the stability of atom. Next, you have dual nature of light. So we have it to be wave nature and particle nature, right? So the wave nature of light, wavelength, distance between two consecutive crest or trough. You would have definitely learned in physics. The wave number defined as the number of waves per unit length, right? And it is inversely, wave number is inversely proportional to the wavelength. Okay, and then you have frequency, number of waves passing through a particular point in 1 second, hertz or per second. Amplitude, the height, yeah, the height of crest or depth of trough, right? The distance traveled between by a wave per unit time. So unit is meter per second. And then you have the electromagnetic waves. The electric field, magnetic field, and propagation of waves are perpendicular to each other. So travels with the speed of light, which is this, and can travel in vacuum. This is your formula that you always and always should know. It comes in handy for any kind of questions. Okay? Yes, and then you have the electromagnetic spectrum. And you have gamma rays, X rays, UV, visible, infrared, microwave, radio waves. So the first three, right? These, sorry, up to until here. These three, high in energy, high frequency, but low wavelength. Why low wavelength but high frequency? This formula. It's inversely proportional. But it is the exact opposite for infrared, microwave, and radio wave. Right? Low energy, low frequency, but high wavelength. Yes. Then you have your particle nature of light. Planck's quantum theory and black body radiation. Black body is an ideal body which emits or absorbs radiation of all frequencies. Radiation emitted or absorbed are in form of small packets or bundles of energy known as quanta or photon. E is equal to h. H is nothing but the Planck's constant, and this is your value. If you just break this V further, you will get C by lambda. Photoelectric effect, emission of electrons from surface of metal by following photon of suitable energy is known as photoelectric effect. The definitions: work function, minimum energy required of for photoelectric effect, threshold frequency, minimum frequency, and threshold wavelength, maximum wavelength required, right? Intensity affects the number of electrons, but frequency affects the energy of electrons. Or you can rather say intensity is quantity, but frequency affects quality. Yep. And then you have the kinetic energy of ejected electron. It's based on the conservation of energy. So the notes are: kinetic energy of ejected electron does not depend on intensity, right? It depends only on frequency. Photoelectric current, or the number of electrons ejected, depends on intensity. So photocurrent does not depend on frequency. It's just the opposite if you see. And Bohr's model. So it solved the question of why doesn't an electron collapse into the nucleus. Bohr's model solved that. There are infinite number of shells in an atom. So an atom consists of two parts, proton and neutron, which has the nucleus, whereas the extra nuclear part is nothing but the electrons. So the electron revolves in a fixed circular orbit. We know that. And then we have the angular momentum, right? MVR is equal to NH divided by 2 pi, and N can be 1, 2, 3, and so on. So ground state is always N is equal to 1. The excited state, shell other than N is equal to 1, right? So the energy of electron increases as we move further away from the nucleus. This is important. Okay, as you move further away from the nucleus, it increases. But the energy difference between two consecutive shell decreases as we go away from the nucleus, right? Please understand this. Now you have the limitations of Bohr model. Applicable only for a single electron species. Could not explain de Broglie hypothesis and HUP. Could not explain splitting of spectral lines in presence of magnetic field, Zeeman effect, and the electric field Stark effect. Right? Um, then you have the important formulas of this entire concept. So, yes, you can look through that. And then you have the ionization energy, ground state, n is equal to 1, infinity shell, n is equal to infinity. And then you have IE, something that you need to learn. Hydrogen spectrum is discontinuous, it's a line spectrum, right? Emission N2 to N1, right? It's from a higher shell to the lower one, higher orbit to lower orbit. So absorption is from lower orbit to higher orbit. Emission is from higher orbit to lower orbit. Absorption is from lower orbit to higher orbit, right? Then you have the series. It's important for you to know the names of at least these five, but specifically know the Balmer series with the number of orbit and region, because it's the visible region, right? The lower orbit is 2 and the higher orbit is 3, 4, 5, and so on, right? And then you have the final formula is this. Dual nature of matter, the Broglie hypothesis. It's the lambda is inversely proportional to p, matter waves, right? Lambda is equal to h by p. P is nothing but momentum, and lambda is equal to h by mv, or p is equal to mv, momentum, if you didn't know that. So yes, you get higher momentum, smaller wavelength, right? And then you have the Heisenberg uncertainty principle. It is important to determine exact position and momentum of electron simultaneously with accuracy. But the problem here is that if you know the exact position of an electron, it's high unlikely that you know the momentum of the electron simultaneously. And that's why it's called uncertainty principle. And then we have the wave mechanical model of atom, right? This is, you just need to understand the Schrodinger wave equation. Yes, and then you have the quantum numbers. Extremely, extremely, extremely important. But also this has the electron behaves as waves. This is an important concept. And then you have the quantum numbers. Very important. Set of 4 numbers which tells us about the energy of electron, sublevel, orientation, and spin. The types are principal, azimuthal, magnetic, and spin. Principal quantum number. Just remember, principal quantum number, it depends on the n, which is nothing but the number of shell or the orbit. So it gives us an idea about the energy, radius, and velocity. The formula is max electron in shell 2n to the power 2. Example, n is equal to 1, k shell max electron is equal to 2 to the power 2 into 1 to the power 2, so you get 2 to be your answer. And then you have the azimuthal quantum number. Blindly remember, azimuthal is equal to shape. So you have shape. So L is equal to 0. S spherical, P dumbbell shaped, D double shaped, and F is complex. Yeah. If a trick to remember is S, P, S0, L is equal to 0, P1, D2, and F3. This is something that I used, right? And then you have magnetic quantum number represented by M, tells us about the orientation of orbitals. Very important, right? It can be -1 to +1. Number of orbitals to L plus 1. Spin quantum number, the spin, it's represented by S, either half 1 by 2, plus 1 by 2, or minus 1 by 2. Each orbital can hold max 2 electrons but with opposite signs. And then you have the energy of electron. Single electron species, energy depends only on n, lower energy. Case 2, multi-electron species, it depends on n plus 1. So rule n plus 1 lower energy, and if n plus 1 is same, lower n has lower energy. Right? And then you have the electronic configuration. Very important rules, something that IMAT normally tests. Okay, the Aufbau rule. Electron fill in increasing order of energy. So basically, they go from the lower orbit to the higher energy. Right? So that's something they should know. The Pauli's exclusion principle. No 2 electrons can have the same values of all 4 quantum numbers. The Hund's rule of maximum multiplicity, pairing occurs only after all orbitals are singly filled, right? So everything has to be filled. And then you have, again, very important, diamagnetic, paramagnetic. Diamagnetic, 0 unpaired. Paramagnetic, at least 1 unpaired. Okay? So magnetic moment, this is your formula. And always remember, never calculate magnetism first. You always have to count the unpaired electrons first. Okay? This is a reason for half filled and fully filled stability. Symmetrical distribution of electron, exchange energy, more stability. And this is your nodes, region where probability of finding an electron is 0. Okay, formulas, radial node n minus L minus 1, angular node L, total node n minus L. The shapes of orbital, s orbital, pinospherical, p orbital, dumbbell, d orbital, double dumbbell. Axial orbital, the shape of d orbital is what they've mentioned here, and the number of waves is equal to orbit number. So the formula is 2 pi r is equal to n lambda. Now let's move on to the PYQs. The PYQs are relatively simpler and easy, don't worry. So how many electrons can occupy an orbital? Okay, remember Pauli exclusion principle. One orbital, not one subshell. Please note that, right? So 2 electrons with opposite signs. And yes, yep, A is your answer. A simple ion, this was for 2025, so it's super easy. A simple ion of element A can be represented as this. How many electrons are represented in this ion? Positive charge is nothing but electron is lost, something that you should know. Always subtract positive charges. And so to find electrons, atomic number minus charge. Yes, and so you get 2xe to be the answer, right? This is something that you should please make note, and it's the opposite for negative charge, electron gained, and you always add when there's a negative charge. And then you have the second question, an atom has atomic number x and mass number so much. How many neutrons does it contain? Neutrons formula. Just write that and then you will arrive at your answer. Yep, x plus 6, which matches D. Tritium has 2 neutrons, equal mixture of isotopes. Find the relative atomic mass. First of all, you should know the isotopes of hydrogen, right? Tritium is an isotope of hydrogen. So these are the isotopes. Please learn this. So equal mixture means simple average, right? It's the simple average. You can connect this with your first lecture. And you calculate the average and you get 2 to be the average. So whenever you see equal abundance, equal mixture, equal percentage, just take the arithmetic mean. And so you have 2 to be the answer. And then you have the next question. Which of the following particles has the same number and arrangement of electrons? Okay. So this again has to go, you have to go option by option. So it's not an ion question, but an isoelectronic question. Electrons is nothing but the atomic number plus and minus charge. You have your charge here, you're right. So lose electron, as I mentioned, you have to subtract. Okay, gain electron, you will add. Okay, so that is what we are doing. We're going step by step. In A, it's not matching because you have the atomic number of oxygen is 8, and because it's minus, you add, you do the opposite basically, and you get 9 electron. You're 2 minus, so plus 2, you get 10, not matching. B, you did the same, not matching. And then you went to C. When we did it like for NA's atomic number is 11, because it's plus, you subtract and you get 10. Same thing, 8 plus 2, you get 10. It's matching, and so you have C to be the right answer. Okay, if you do not understand this part, you will not be able to solve any of this question. So please make note, you understand this and learn that lose electron, you subtract, gain electron, you add. Okay, the signs are really important. And And yeah, this is our last slide for this chapter. Which of the following particles has the same number of neutrons as this ion? Charge changes electrons, therefore not neutrons. Okay, so neutrons is A minus Z. You got it to be 44 neutrons for this particular element. And so when you are trying to find for each of it, you can see the charge. They've given it on purpose for to confuse you. So please don't get distracted by the charge because it only influences the electrons, not the neutrons. So does not match. For B again does not match, but for C you have 44. Direct. Go ahead with that. Okay? These are the little tips that you should know. If not, you will mess up the entire question. The last question: an atom has a mass number of 18 and contains 10 neutrons. A common ion of this atom has a charge of -2. What is the electronic configuration of this ion in its lowest energy state? Okay, yeah. So mass number is 18, neutrons is 10, ion charge is -2. You find A, Z plus N, you get Z, right? The atomic number. Now the negative means gain of electrons, so you add it, you get 10. And that's that. Yes, to write the electronic configuration, there's a tip that I would like to give y'all is yes, for these you can write to remember, right? You can write school to remember. So school, 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 public, sorry, public school, public school, district public school, and again, district public school. Obviously, I'm writing this down in full so that you know what I'm telling, but in your mind, you can automatically, when like during the exam, you can say school, school, public school, district public school, and then all you have to do is you add the numbers. So 1, 2, first you go for S, 3, 4, 5, and 6. And for when you're starting for P, you go with the second number. Here you started with 1, so you start with 2, 3, 4, 5. And for D, you because you started P with 2, you go with the next number. So 3, right? 3, 4. And that's how you do it. And that's the trick I used because I found it hard to remember all this when I was learning. But yes. So that's that. Once you use that, you will definitely get that 1s2, 2s2, 2p6. Yep. Yes, and that matches D.
If you want me and my team to help you out with the academics and also the documentation processes for the IMAT exam, you can fill the form below and my team will get in touch with you through
So
WhatsApp.
now let's move on to the next chapter, that is redox reaction. Okay, redox reaction is a very simple, easy chapter. You just need to know the concepts well, and you can solve any kind of questions. And I guarantee you, there will be at least one question from this particular unit, as you can see, at least one from the past few years. So it's important, right? Now we have the basic definitions. What is oxidation? The increase in oxidation number. Reduction, decrease in oxidation number. Oxidizing agent or oxidant. Oxidizing agent is also called as oxidant. Okay, a reagent which can increase the oxidation number. Okay, agent. What is an agent? Someone who helps the other person to do something. To they cater to the needs of the other person. So basically, they oxidize the others, but they reduce themselves. Okay, the same way, reducing agent, they reduce others, but they oxidize themselves. Okay, and then you have redox reactions, reactions which can involve change in oxidation number of the interacting species. A tiny trick to remember oil rig is oxidation, loss of electrons, rig, reduction, or is gain of electrons. The types of redox reactions. You have combination reaction. A redox reaction in the form A plus B is equal to C, just direct combination, is a combination reaction. Okay, then you have decomposition reaction, breakdown, decomposition. So, breakdown of a compound into two or more components, at least in one elemental state, right? And then you have disproportionation reaction. An element in one oxidation state is simultaneously oxidized and reduced, must have at least three oxidation states, right? And then you have displacement reaction. So, yes, very simple, x plus yz. It gets displaced and you have xz and plus y. Okay, so metal displacement, a metal displaces another metal from its compound. It depends on the reactivity. Higher one displaces the lower one. Yeah, then you have the non-metal displacement. Non-metal displaced by metal or another non-metal. Same thing. And then you have comproportionation reaction. Element in higher plus lower oxidation state, it gives you an intermediate oxidation state. Balancing of redox reaction. Identify oxidation and reduction, right? Very important. First step. Equalize the total increase and decrease in oxidation number. Third, balance atoms except oxygen and hydrogen. So in acidic medium, oxygen balances with H2O. Hydrogen balances with H plus. But in basic medium, oxygen balances with H2O and charge balances with OH. So this is the difference. Oxidation number rules. Very, very important. Element in the free state is 0. Okay, for example, H2, O2, they're all in the free state, right? So it is has an oxidation number of 0. The sum of oxidation number in a polyatomic ion is equal to the charge on ion. So usually oxygen is -2, peroxide is -1, superoxide is -1 by 2, and in O2F2 it is equal to +1, in OF2 +2. Okay, and then hydrogen is usually +1, in metal hydrides -1, fluorine always -1, the halogen group, alkali metals, that is the first group on the periodic table, +1, alkaline earth metals +2, the second group on the periodic table. The sum of oxidation number in a compound is equal to 0. An example here. Okay, and now is just the important concept. Highest oxidation state, reduction, oxidizing agent. Okay, lowest oxidation state, oxidation, reducing agent. Intermediate can act as both. Points to remember: carbon suboxide, CrO5 structure, peroxo compound, tribromo oxide, tetrathionate ion. Not of that importance. It's never given in the IMAT thing. So you just have to go through these points. Not important. Yes, now we move on to the PYQs. Now you will know why I said that it's really easy. So in which of these compounds does C-Hel have an oxidation number of +3? Again, 2025. You go step by step. So start with A. When you try to solve the oxidation number of Cl, you get it as 3 and you stop right there. We know H is +1, O is -2. So -2 into 2, you get -4. You take the one that you have to find as X and you find the oxidation number. An oxidation number cannot be, again, 2025. You can see 2 questions from this particular unit. It cannot be an irrational number, right? It can be a negative number, it can be a positive number, a number with a decimal point, and even a 0. We know that for a compound it's 0, but never and never an irrational number, right? This reaction is used in the extraction of titanium from its ore, that is this. Which substance is or slash are the reducing agent in this reaction? Okay, reducing agent, as I mentioned, it oxidizes itself but reduces others. So when you see C, carbon, in the reactant has 0 oxidation state. but in the product it has +2. And so there is oxidation. So first ask, who is oxidized? Carbon, 0 to 2. So oxidation. Again, reducing agent reduces others, oxidizes itself. Oxidizing agent oxidizes others, reduces itself. This concept is very, very important because they basically test you on this particular thing, as it's easy for students to get confused. So please go through this and you will understand to solve any kind of questions. So yes, obviously, which one is that I use reducing agent here? It's carbon. All right. Next, we have consider the reaction. This. Which one of the following describes the role of HNO3 in this reaction? Okay. So if you try and calculate the oxidation number of both sulfur and nitrogen in this particular reaction, you get it to be the same. And so what does that mean? There was no oxidation or there is no reduction. And so it can only be proton transfer. Okay. So who received the proton here? It was the base, if you can see. And so it's the base. So which of the following describes the role of HNO3 in this reaction? HNO3. And if you can see, there is a plus here. And so it's receiving a proton. A base always, base receives proton, right? It receives proton. You will learn again in ionic equilibrium. And so it's a base. HNO3 acts as a base. And then you have, which of the following equations represent redox reaction? Okay, we have 3 equations. So we have solved 3 of them. And let's see. So Li in the first reaction is +1 everywhere. Okay, Al is +3 everywhere, Cl -1 and H -1 everywhere. Okay, so there was no oxidation change, and so it is not a redox reaction. But the second one, N in N2O3, you have it to be +3, and again in NO2 minus, you have it to be +3. No oxidation change, and therefore no redox reaction. But in the third equation, N in NH4 plus ammonium is -3. But in case of the N2O, in case of product, it is +1. Obviously, there is an oxidation, right? And so there is a redox reaction because N in NO3 minus, X is +5, but here +1. There is a decrease, but there is also an increase in the oxidation number, right? And so third is a redox reaction. So 3 only. Zinc nitrate, nitrogen dioxide, and water are obtained from the reaction of metallic zinc and nitric acid in aqueous solution. What is the reducing species? As I said, they only rotate around these kind of questions. So please understand this. So who is the reducing species? Reducing, right? So you have to find the oxidized species. So find who is oxidized. Zinc. If you write down the equation and try to find the oxidation number, zinc by itself is 0 and that gets increased to +2. It's oxidized and therefore zinc. The compounds of chlorine include Cl2, this. Which one of the following option correctly lists the oxidation state of chlorine that are shown in these compounds? Very easy, direct calculation. Okay, so when you find, you will get KCl -1, Cl2 +1, and then here +1, +5, +7, +7. You can directly match it to be with this one. Yes. And this is an extra tip that you can not memorize, but it can come in handy, you never know. HClO, you have +1. HCl, the oxidation number of Cl here is +3. Here it is +5. Here it is +7. Alright, so with this we are done with redox reaction. So please remember this particular tip. Very, very important, and oxidation number calculations, you'll be good to go. Now we have gaseous laws, a relatively simpler and easier chapter. It just has a lot of theories or formulas with that, and application of formulas in questions, because that can be a little tricky, but otherwise it's a wonderful chapter. So let's get started. Basic properties has three main properties: volume, temperature, pressure. And the units, very, 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 very important. They can just ask you just bluntly the units as a part of the MCQ, because I remember in 2024, there was a question about pressure that just had what are the units of pressure, and there were options. So it's really important you go through the units, right? So, yes, and never ever use Celsius in gas law calculation. I'm sure you know that. Please convert to Kelvin always. Avogadro's law: under similar conditions of temperature and pressure, equal volumes of gases contain equal number of molecules, and therefore the volume of gas is directly proportional to moles. Okay, and this is your equation. Please remember. Ideal gas equation: PV is equal to nRT. So R is 0. The universal gas constant. This is the value, and these are the values in different units. Again, important to know because the question might be anything at all. So very, very important you know and learn these values. The density of gas, D, is equal to Pm divided by RT, pressure, molarity divided by RT. So as density increases, pressure increases. You can see this. Boyle's law: P, pressure, is inversely proportional to V, okay, at constant temperature. And this is your formula. We have Charles' law. I can give you an example of a hot air balloon. It rises as the volume increases, temperature increases. And so, again, it's at constant pressure. Please remember. Absolute zero. Absolute zero is important because they might just give you bluntly at absolute zero. They might not tell you the temperature specifically, for example, 273 or 0 Kelvin. They'll just mention absolute zero. Please don't forget to either put in 0K or 27. You normally don't put in Celsius, but know the values. Then you have the Gay-Lussac's law. In Gay-Lussac's law, if you see a rigid cylinder, fixed volume, closed container, just blindly remember it's Gay-Lussac's law. Pressure is directly proportional to temperature at constant volume. Okay? And then you have the Dalton's law of partial pressure. Its P total is equal to PA plus PB beta plus PC. It's just the summation of the three. Okay, the validation of Dalton's law: valid only for non-reacting gases at room temperature. Okay, so it is valid only for H2 plus O2 valid, NH3 plus HCl invalid. These two are not of great importance. You can just go through them. It's the Graham's law of diffusion and the calculation of diffusion. There is no question so far on this. So just go through it, right? And then you have the average kinetic energy. It depends only on temperature. This is very important. There are questions based on this in your PYQs. Concentration might change, volume might change, anything might change, but if there is no change in temperature, it does not affect the kinetic energy, right? And this is for 1 mole, the calculations for 1 mole, or the formulas for 1 mole, n moles, or one molecule, right? The Maxwell Boltzmann distribution, important. Okay, it's a graph that has the fraction of molecules on the y-axis and the molecular speed on the x-axis. So MPS lesser than the RMS. Okay, I used to remember this as Mars, the Mars chocolate. So, but remember it's lesser, right? And this is the effect of temperature. When temperature increases, curve shifts towards the right side. So the peak lowers, can you see? But the area remains the same. Okay, important notes, theory points. Kinetic theory of gases. Gas is made up of large number of tiny particles called molecules. The effect of force of gravity on gas molecules is negligible due to their very small mass. Particles of gas are in constant random motion. Now, this is where the important part starts. Collisions are perfectly elastic in nature. Okay, very, very important theory point: elastic. Average kinetic energy of a gas sample depends only on temperature, as I mentioned. volume occupied by gas molecules is negligible in comparison to the volume of container. Okay? And there is no force of attraction between gas molecules. And so they are in constant motion. Molecular speed, please go through this. Right? Effect of temperature. On increasing temperature, the entire curve shifts toward right. Most probable speed increases. The fraction of molecules having most probable speed decreases. Area under curve remains the same. Next, you have a real gas. Okay, gases which do not follow PV is equal to nRT at all temperature and pressure. So, note a gas behaves as an ideal gas only under two conditions. Okay, under low pressure and high temperature. Very important. Okay, this is very important. Theory point. So, it behaves as an ideal gas only when there's low pressure and high temperature. And then you have the van der Waals equation. Not very important. Never seen a question based on this. Just go through this. You're good to go. Compressibility factor. Z is equal to PV divided by nRT. Z is nothing but the compressibility factor. Z is equal to V real divided by V ideal. Volume real divided by volume ideal. Okay, so when Z is equal to 1, that is nothing but in case of an ideal gas. And so you'd use the ideal gas equation. Okay, and when Z is greater than 1, higher pressure, and so it's a positive deviation. V real is greater than V ideal, and so this will be your formula. But when Z is lesser than 1, lower pressure, negative deviation, and so V real is lesser than V ideal, and this becomes your formula. Liquefaction condition. To liquefy a gas, you need high pressure, low temperature. Important. These are the kind of theory questions that can arrive in your IMAT. And next, you have your Boyle's temperature. Temperature at which real gases obey ideal gas over a wide range of temperature. Right? That's your Boyle's temperature. Critical constants. Okay, you have two, that is critical temperature, critical pressure. Temperature above which gas cannot be liquefied, however high pressure is applied. That is your critical temperature. Critical pressure, minimum pressure that must be applied on a gas at critical temperature to liquefy. Inversion temperature. Inversion temperature is nothing but your Joule-Thomson effect. So temperature at which there is no heating or cooling of gas. So there's no heating or there's no cooling. So occur during adiabatic expansion, right? Yes. So now we move on to the PYQs. You can see how easy the PYQ can get. 2025, the equation of state for ideal gas. PV is equal to nRT. That easy. Next question, a gas in a rigid cylinder. As I mentioned earlier, you see rigid Gay-Lussac's and maintained at a temperature of minus 3 degrees Celsius exerts a pressure of 9 atm. What pressure would the same gas exert if it were heated at 27 degrees Celsius? First tip, rigid, so Gay-Lussac's. Second, don't forget to convert. Okay, so once you do that, once you convert, you will have to apply the Gay-Lussac's formula. And once you're done with that, you get P2, which is nothing but 10 atm. So we have B to be the right answer. The next question, a sample of n moles of an ideal gas is contained in a closed system of fixed volume, so much, at pressure, so much, and temperature, 27 degrees Celsius. If the gas is heated to so much, what will be the pressure in PA at this new temperature? Fixed volume, closed system. Okay, these are the hints. So N constant, V constant. P is directly proportional to temperature. Again, always convert T to Kelvin. And so once you do that, you can apply the formula. And you get P2 is equal to 2P, right? So you have C to be the option. The next question, an ideal gas is at a temperature of 10 degrees Celsius. At what temperature will the pressure of the gas double, assuming the volume remains constant? P doubles, V is constant, therefore P is directly proportional to T. Convert into Kelvin, and once you use that, you will get the answer to be 293 degrees Celsius, because the option comes in degrees Celsius, 10 degrees Celsius, so you have to give the answer also in degrees Celsius, right? And obviously the options also say the same. So 293D is your answer. You have a mixture of 0.3 moles of N2, 0.5 moles of CO, and 0.4 moles of O2 exerts a pressure of 2.4 atm at 22 degrees Celsius in the vessel that contains it. What is the pressure exerted by the nitrogen? Partial pressure is equal to mole fraction into total pressure. And so once you apply the same, because this is you're finding mole fraction of 1 divided by the total, you get this value. And next you find the pressure, the total P of N2, you get 0.6 atm. So you have D. The next question, this is the reaction. If 150 centimeter cube of F2 reacts with 100 centimeter cube of Cl2, what is the final gaseous volume at the same temperature and pressure? So you use coefficients directly. Volume ratio is equal to the mole ratio. You use this equation, whatever is given. Limiting reagent first. So you find the limiting reagent. The limiting, you have the volume here, and you divide it by the coefficient. You have 50 centimeter cube, 100 centimeter cube. Obviously, this is limiting, right? So F2 is entirely consumed. So Cl2 remaining is 100 centimeter cube minus 50 centimeter cube, which is equal to 50 centimeter cube. And so that is remaining in the reactants side. So products produced based on stoichiometry, we know that 150 into 2 by 3. 150 is this one, 150, because it is a limiting reagent and you solved everything based on the limiting reagent, 150, right? And 2 is here. So you're solving for ClF3. So 2 divided by 3, that is this 3 from here, into 150 again from F2. Alright, and then you get 100 centimeter cube of ClF3. So the total is remaining Cl2 plus ClF3, which is nothing but 150 centimeter cube. Wasn't that a nice question? So it's a combination of your limiting reagent and trying to apply, because if you miss out on not adding the Cl2 remaining, you will arrive at the wrong answer. So because 100 is an option in the question. Yes. Yeah, with this we're done with gaseous state. Now let's move on to chemical equilibrium. We now have chemical equilibrium, a really favorite chapter for IMAT. So really easy. Please understand the concepts. You're good to go. What is equilibrium? The chemical reaction which takes place in both directions are called reversible reactions. Equilibrium is the end state of a reversible reaction. So gaseous equilibrium is established only in a closed container. So at equilibrium, the rate of the forward and the backward reactions are equal. At equilibrium, the concentration of the reactants and products become constant. So this is an important point. So they can ask you that at equilibrium the rate becomes equal, but does the concentration become equal? No. So important to know that it becomes constant, the concentration becomes constant, but not equal. This is a graphical representation. Because it's a forward reaction, the reactant decreases and the product increases eventually, right? In this case. Yes. So forward rate with time, it decreases. Backward rate, it increases with time. Now you have the physical equilibrium. Such equilibrium is established in physical reactions. It is dynamic in nature, which means it can change. So liquid vapor equilibrium, your vapor pressure is constant at a constant temperature. Solid liquid equilibrium, established only at a constant temperature. Melting point of solid, that is freezing point of liquid, established only in a saturated solution, right? So solid in a liquid equilibrium, established only in a saturated solution, saturated sugar solution, right? Sugar dissolved, sugar undissolved. So, gas in a liquid equilibrium. Here, solubility depends upon pressure, the Henry's law, if you remember, right? So, soda water, example, soda water. Now, the chemical equilibrium, important. So, the chemical equilibrium approaches from both forward and backward direction. Chemical equilibrium is dynamic in nature because of this property. So, the equilibrium constant K is nothing but for a general reversible reaction. So, you write the products on the numerator with the coefficient as the power divided by the numerator's concentration to the power of the coefficient of the numerator, right? So, at equilibrium, Q is equal to K. So, the ratio of this is known as concentration coefficient, which is Q. And so at equilibrium, Q is equal to K. Very important. Properties of K. The value of K does not depend on initial concentration of reactant or product. The value of K does not depend upon the direction from which the equilibrium is attained. K for the reaction, this will be K to the power N, right? And if K for the reaction is K, then value of K depends only on temperature, like we did in the previous chapter. So if K for the reaction is K, then K for the reaction will be 1 by K. What is the difference? This is basically the switch. So the product becomes a reactant, the reactant becomes a product. That's the difference, right? So here it's K, here 1 by K. During the addition of two reactions having equilibrium constants K1 and K2, then the net constant K is equal to K1 into K2. You multiply when it has to be added. During the subtraction of a reaction having constant K2 from a reaction having constant K1, then the net constant will be division. So K1 divided by K2. Important. If Q, the reaction coefficient, is lesser than K, the reaction will proceed in the forward direction. And so more products will be produced than more reactants. If Q is greater than K, the reaction will produce in the backward direction, and so more reactants will be produced than products. Q is equal to K, the system is in equilibrium. If K is greater than 10 to the power 3, the reaction is almost complete in forward direction. But if K is lesser than 10 to the power minus 3, the reaction is almost backward. If K is in between 10 to the power 3 and 10 to the power minus 3, almost same reaction takes place in both the forward and the backward direction. I know it's a lot of theory, but yes. Kc and Kp. If they are in solid or liquid phase or even aqueous phase, K can be represented as Kc. If they are in gaseous, K can be represented as Kp as well as Kc. Important. Very important. Okay. So this is how you write for both Kp and Kc. Kp, you are taking pressure. Here you are taking Kc, so concentration, concentration, concentration of everything. Here you are taking pressure of each of it. So the relation between Kp and Kc, important. Kp is equal to Kc into RT to the power n. Okay, n is equal to Np minus Nr. The unit is this. Unit of Kp is this. So if n is equal to 0, equilibrium constant has no unit. Heterogeneous equilibrium. Heterogeneous, more than 1. So in heterogeneous equilibrium, concentration of pure solid and pure liquid is taken as 1. Right? So it is in two different states basically. Lee-Chatelier principle. Very important. According to Lee-Chatelier principle, if a system at equilibrium is subjected to a change in concentration, temperature, or pressure, the equilibrium will shift automatically in one direction, which will nullify the effect of change. Okay, so it's always trying to reduce that change. So how does it affect concentration? Concentration of a reactant increases, it shifts towards the forward. If the product decreases, shifts towards forward. If the concentration of the reactant decreases, it shifts towards a backward direction. But if the concentration of product increases, it shifts towards the backward reaction. Now we have the effect of pressure. Same thing. Pressure increases, shift towards a lesser number of gaseous moles. Okay, so it's almost like pressure is inversely proportional to number of moles. So please understand this, very important. Pressure decreases more, so towards shifts towards higher number of gaseous moles. So if number of gaseous moles of reactant and product are equal, pressure has no effect. Effect of temperature. If temperature increases, shifts towards endothermic. Endothermic is when the H is greater than 0, right? Exothermic is when the H is lesser than 0. So if temperature decreases, shifts towards exothermic. Catalyst. It helps to attain equilibrium state easily. After the establishment of equilibrium, catalyst has no effect. Okay, so it basically increases the rate, but otherwise catalyst does not take part in the reaction. Inert gas. Addition of inert gas at constant volume, no effect. But the addition of inert gas at constant pressure shifts towards higher number of gaseous moles. Very, very important. Yeah. Volume, no effect. Constant pressure shifts towards higher number of gaseous moles. This is again important. Chapter in a gist, I would say. Please go through this and understand what change does each of these properties bring about. All right. So now let's solve the PYQs. Given the equilibrium, heat plus 2FeCl3 gives you 2FeCl2 plus Cl2. So 2025 question. Which of the following options is correct? Okay. So firstly, heat is on the left, right? You can see that. So the forward reaction is endothermic. And it's an important point. Pure solids are ignored and do not affect equilibrium. Can you see that? Not just solids, even liquids, if it's a pure solid or a liquid, it is ignored and it does not affect equilibrium. It's just gas that affects the equilibrium. To shift the equilibrium to the left, it is necessary to increase the concentration of Cl2 gas. To shift the equilibrium to the left, you increase the concentration of C. Yes. So this is option A. Let's go through the others too. To shift the equilibrium to the left, it is necessary to increase the concentration of FeC. You see solid? No, definitely no. FeCl3, the third option. No, so no effect. To shift the equilibrium to the right, it is necessary to cool the reaction. No effect. To shift the equilibrium to the right, it is necessary to increase the concentration of FeCl3. It shifts to the left and not to the right. And again, yeah. So, no effect. Next question. At a given temperature, the Kc value of a gaseous exothermic reaction is equal to so much. Which one of the following statement is correct? So, K is equal to 7 into 10 to the power of minus 3. And as we learned before, if K is less than 10 to the power of minus 3, what is formed is mostly reactants. Okay? Exothermic reaction, and so lower temperature, higher the K. There are moles on the right hand side of the equilibrium equation. No. Addition of a suitable catalyst will increase the equilibrium yield obtained. Definitely no. The position of equilibrium lies over to the right hand side. No, because it's just reactants, mostly reactants, so no. At a lower temperature, the Kc will increase. Yes, because it's in case of the exothermic reaction. So yes, at lower temperature, Kc will increase. That's true. So D is the right option. Let's go through E as well. An increase in pressure will increase the time taken to reach the equilibrium. No, this has no relation at all. So no. The next question, which statement explains melting of ice with sugar? And before I forget, you will understand why I said low temperature exothermic. There's a question that's coming up in the next slide. So you will understand that time, right? Which statement explains melting of ice with sugar? Sugar is an impurity. So impurities lower the melting point of ice. Let me give you an example. Some countries they add salt on a roll which has ice on it. Why is it? Because it lowers the melting point. So option 3, melting point lower, doesn't higher the melting point. Sugar, no, sugar doesn't give energy. So option C is the right answer. And this is the question that I was mentioning, the second question that we did. In exothermic conditions, the Kc decreases with the temperature increase, but the Kc increases with temperature increase. And this is in case of exothermic. But in case of endothermic, Kc decreases, temperature decreases. Kc increases, temperature increases. Simple. Okay, this is the application that I used in that question. Which factor increases Kc? Blindly, just temperature. Just score out all the others. Now, whether it's decrease in temperature or increase, you will only know if it is exothermic or endothermic. Since none of that is mentioned, it's a little tricky question because you don't know. There's no proper data that's provided. I would always choose exothermic because that is something that's more asked, or rather that's more common. So yes, I would rather choose exothermic and so decrease in temperature for increase in Kc. Yes, there's no enough info for this question. A mixture of methanol and ethanoic acid is left until equilibrium is reached. The equation for this reaction is given below. So you can see your delta H to be minus in minus. So hope that triggers something. Exothermic. The amount of CH3OH in this mixture of equilibrium can be increased by adding more water to the mixture. Okay, so water is a product, if you can see, right? It's a product. So adding product shifts equilibrium backward, produces more CH3OH. And so it is raising the temperature of the mixture. Delta H is negative, so forward reaction is exothermic. If we increase the temperature, equilibrium shifts backward towards the reaction. So, yes. Adding NaOH to the mixture. When NaOH reacts with ethanoic acid, it removes it. And so, when a reactant is removed, equilibrium shifts backward to replace it. And so, it increases CH3OH. 3 2. Adding a catalyst to the mixture. Faster only, no yield change. So 1, 2, and 3. It's part of the options. Yes. The last question. P, Q, and R represent substance involved in a gaseous reaction. The equilibrium constant Kc and the sign of the enthalpy change for the reaction are Kc is equal to this. Delta H is negative. Exothermic. Assuming that all the other conditions remain constant, a change in which factor results in an increase of the value of the equilibrium constant Kc. Kc. So think K only changes with temperature like we did. So delta H is negative, exothermic. Exothermic loves cold, and so temperature decreases. Therefore, forward reaction favored and K increases. So what is the answer? A decrease in temperature. So that is your answer. Okay, so we are almost midway in our lecture. So I hope you are not tired. Please take a break and drink some water. Okay, but yes, now we have ionic equilibrium, one of the most important lecture in the entire syllabus because it helps you connect various topics. Like a question can have anything with ionic equilibrium concept in it included. So please understand it well. Firstly, ionic equilibrium. Undissociated becomes dissociated. You can see it's undissociated, and here you can see it's dissociated into ions. So a negligibly ionized or dissociated equilibrium is established. The equilibrium established between the dissociated part and the undissociated part is known as ionic equilibrium. The classification of substances as electrolytes and non-electrolytes. So substances which dissociate into its component ions is electrolytes, whereas non-electrolytes which does not dissociate into its component ions. You can see it remains the same in the reactants and in the products. The other examples can be H2, N2, O2, and also glucose, your organic compound, sucrose, all of that comes under your non-electrolytes. Right? Now you have the classification of electrolytes. Strong electrolytes, weak electrolytes. Strong electrolytes, 100% ionized, and the degree of dissociation is 1. This is extremely important. The six strong acids and the six strong bases. This helps you in solving many questions that come out of this chapter. So please mug up all of this, right? You should know what are the strong acids and what are the strong bases. And the salts, strong electrolytes is NaCl, NH4Cl, CH3COONA. Weak electrolytes. Anything other than the strong acids and the strong bases is a weak acid and a weak base. Here, the degree of dissociation is less than 1. And now we move on to the theories. The Arrhenius acid base theory. Here, the acid is any substance which gives H plus ion in water, while the base is any substance which gives OH minus ion in water. The limitation is that it's limited to aqueous solution. It cannot explain acids and bases without H plus and OH minus ions. Now we have the Bronsted-Lowry theory. Here, acid is an H plus donor, not an ion but a donor, but base is an H plus acceptor. Okay. Here you have the conjugate acid base pair having difference of one H plus ion. Here there is acid HCl, but here there is a difference of H, and so this is the conjugate acid and this is the conjugate base. But here it is a conjugate base because here there is an addition of hydrogen ion, and so it's a conjugate acid, right? So if acid is weak, then its conjugate base is strong and vice versa. Weaker the acid, stronger the conjugate base, and stronger the conjugate base, weaker the acid. Limitation, it cannot explain acidic nature of AlCl3, BF3, etc. Lewis theory, another important theory. Acid is an electron pair acceptor according to this theory, and base is an electron pair donor. We saw ion, we saw H plus donor acceptor, but now we see it's an electron pair acceptor and base is an electron pair donor. Okay. The types of Lewis acid: incomplete octet, right? D block cations, the empty d orbitals, multiple bonds. Not that important. Types of Lewis base: neutral molecule with one lone pair, negatively charged ions. Just an example for you to understand. Limitations: fails to assign strength of acids and bases. Reaction should involve coordinate bond formation. Now you have your water and ionic product. Water is a very weak electrolyte. Okay, so the Kw is nothing but the concentration of the H plus into OH minus. So at 298 Kelvin standard temperature, Kw is equal to 10 to the power of minus 14. Very important formulas come in very handy. Okay, when the H plus concentration is equal to the OH minus concentration, neutral. So the pH is 7. Whereas when the H plus concentration is greater than the OH minus, it's acidic, obviously. And so the pH is less than 7. When the H plus concentration is lesser, basic, which is nothing but the OH minus ions is greater, right? And the concentration. So the pH is greater than 7. Equilibrium constant depends only and only on temperature. I think it's the millionth time that we are talking about that. So increase in temperature, Kw increases. Dissociation of H2O increases. pH scale. We have really important formulas here. You need to and have to learn it thoroughly. Okay, so pH is equal to minus log H plus concentration, POH minus log OH concentration. Okay, pKw is equal to pH plus POH. At 298 Kelvin, pKw is equal to 14. Okay, ionization of weak electrolyte. Ha plus H2O gives you H plus A minus. So Ka is equal to, like we did, the products divided by the reactant. For weak electrolyte, Ka is equal to Ca alpha square. So the hydrogen concentration is equal to root of Ka into C. pH is equal to half pKa minus log C. One important tip: weak acid pH questions, Ka plus and concentration is given, directly use this formula. This is all for weak electrolyte and you have to learn it, unfortunately. Okay. The relation between Ka and Kb: Ka into Kb is equal to Kw. pKa plus pKb is equal to pKw. At 298 Kelvin, pKa plus pKb is equal to 14. Has to be learned. Common ion effect. When you hear the word common ion, remember solubility. Presence of common ion decreases solubility. More the common ion, lesser the solubility. So therefore, it's inversely proportional. All right. Solubility equilibrium. AgCl gives you Ag plus Cl minus, and Ksp, nothing but the solubility product, is equal to this. You have the products. Sparingly soluble salts, example, are the following. Right? And now you have the relation Ksp is equal to S square for 1:1 electrolyte. For example, Na plus Cl gives you NaCl. Right? It's a 1:1 relation. And so Ksp is equal to S square. Ionic product. If IP, ionic product, is lesser than Ksp, no precipitation. So IP is equal to Ksp, saturated. IP is greater than Ksp, precipitation. This is the order. Just understand. Alright, now you have the buffer solution. What is a buffer solution? It basically acts like a chemical shock absorber. So a solution whose pH does not change on addition of a small amount of acid or base or on dilution. Buffer range, the range of pH over which buffer is effective. And the types of buffer: simple buffer, mixed buffer. Salt of a weak acid and a weak base is nothing but a simple buffer. Weak. I hope you remember weak. Okay. Mixed buffer, you have acidic buffer, basic buffer. In the acidic buffer, weak acid and its salt with a strong base. You can see CH, acetic acid. It's a weak acid, but it's a salt of a strong base. So the pH is less than 7. All right. And now you have basic buffer, right? Weak base and its salt with a strong acid. You have NH4OH, which is a weak base, and NH4Cl, which is a salt. It's a salt with strong acid. And so the pH is greater than 7. So it's a basic buffer. Buffer action. It resists the change in pH on addition of a small amount of an acid or a base. The buffer formulas: acidic buffer, pH is equal to pKa plus log salt divided by acid. One tip that I would give you is also, while you are solving these kind of questions, please make sure you do not use the calculator. Let you use a calculator. The log values, if there are any kind, will be given in the question mostly. But maybe you could put the effort to learn at least the log values of the first 10, maybe of log 1, log 2, log 3. It would be helpful some way. Okay. And the basic buffer, POH is equal to pKb plus log salt. Here you have acid, here you have base. That's it. Salt hydrolysis, salt plus water gives you acid and base, reverse of neutralization. Types of hydrolysis. I think in the very first chapter or the second one that we discussed hydrolysis, the strong acid, strong NaCl, or yeah, NaCl, I think, yes. So strong acid and strong base becomes neutral, NaCl, right? NaOH, it comes from NaOH and HCl. So it's a strong acid and strong base. Weak acid, strong base, basic buffer. Strong acid, weak base, acidic buffer. Weak acid, weak base, it depends on the Ka and Kb. Okay. This is the key relation. Ka is greater than Kb, acidic. Kb is greater than Ka, basic. Ka is equal to Kb, neutral. Remember, the hydrolysis always happens because of the weak part. Yes, at 298 Kelvin, pH is equal to 7 for neutral solution. This is an example for you to understand. Like I mentioned, NH4Cl, weak base, strong acid, HCl, so acidic acid. CH3COONA, weak acid, acetic acid, if you can see, and strong base. And so it's a basic. Right? Yep, now let's move on to the PYQs. The pH of an aqueous solution of a monoprotic weak acid with the constant Ka is equal to so much and concentration so much. Direct application. Okay, you just need to apply this and you will get the pH to be 4. It's the weak acid. If you remember, I had mentioned here, yes, this formula, right? It's a direct application that you have to use. Yes, and what is the pH of a 0.7 aqueous solution of KBr? Firstly, KBr comes from KOH, which is a strong base, and HBr, which is a strong acid. And so strong base, strong acid, it's a neutral solution. And so 7. So this is just trick that they're using to confuse us. So once you see this, directly use it and you will get the answer. Right? Next question. According to the Bronsted-Lowry theory, which of the following statement is correct? A base is a compound which can donate OH minus ions. No, that was not in Bronsted-Lowry. That was in Arrhenius, right? So this is not the option. The conjugate base is formed by an acid that has acquired an OH minus ion. Definitely no. The conjugate acid is the product of the bonding of the base with the OH ion. No. A strong acid forms a conjugate with a weak base. Indeed, right? Strong acids form conjugate with weak base, whereas weak acid forms the conjugate with a strong base, and so it is D. An acid is a substance which can provide a pair of electrons. No. They're just trying to confuse all of this with you, but you should know that D is the right answer. Okay? Which one of the following acids are weak? As I mentioned, strong acids and strong bases is something that you should know. So once you remember that list there, you know anything other than that is in the weak section. HCO3 minus. So definitely it is weak because it doesn't fall under the list. HCOOH. Yes. And HNO3 is a strong acid. So 1 and 2 are weak. Yep. E. All right. So now we have the next question, and this is a really, really good question. A few drops of the universal indicator were added to NaOH, then HCl was added. Okay. What color changes occur? The wordings are extremely important here. A few drops of universal indicator were added to NaOH, then HCl was added. It doesn't say that it stops eventually. So what happens? NaOH, as we know, is a strong base, and therefore violet is definitely the first color. So A, B, and C are ruled out. The second is HCl. It's a strong acid, right? It doesn't say that until neutralization stops, or there's no mention as such. Therefore, it will go beyond the neutral point. I hope this reminds you of the other question that we did in solutions, I think. So in that question, it stopped at 7 because a lot of NaOH was added and only a certain amount of HCl was added. And so it stops right there because it gets consumed. But that isn't the case here. It's equally added and therefore it goes beyond the neutral pH. And so you have violet, you have blue, you have green, beyond that, yellow, orange, and red. Okay, this has nothing to do with hydrolysis, so please don't get confused about that particular part here. Next question. Pure water self-ionizes. This endothermic reaction is represented by the equation this. Which of the following statements is true for pure water between the temperature of 0 degrees Celsius and 100 degrees Celsius? The concentration of H plus and OH minus are equal between 0 degrees Celsius and 100 degrees Celsius. And that is true because for pure water, it's in the case of pure water, and so the concentrations are equal. So 1 is true. An increase in temperature causes the pH to fall. Increase in temperature. Yes, because a Kw increases, right? An increase in temperature causes the electrical conductivity to decrease. No, because more ions means the conductivity increases. We have 1 and 2 to be the right answer. So it's option D, right? This is a tip. Pure H2O remains neutral, but neutral pH is not always 7. Okay, the last question for this chapter. Which one of the following 0.01 m aqueous solution has a pH greater than 7? Therefore, it should contain a strong base or it should be a base. So AlBr3 is acidic, so no. NaI is neutral, no. NH4Cl is acidic, no. Na2CO3 is basic because CO3 2 minus comes from weak acid, which is H2CO3, whereas Na2 comes from NaOH, and therefore T is basic. But the last one, CH3CO2H, is acidic, right? So we're done with ionic equilibrium. Let's now move on to chemical kinetics. All right. So in chemical kinetics, let's first go through there's hardly any questions that we could pull out from chemical kinetics. There's just one that appeared last year, but yes, let's go ahead. So the rate of a chemical reaction, the decrease in concentration of reactants divided by the time taken, or the increase in concentration of product divided by the time taken, is nothing but the rate of the chemical reaction. Okay, and here you can see average rate. Consider a reaction A plus B gives you C plus D. The reactants are always having a negative sign. And why is that? Because over time, eventually, the reactants decrease, while over time, products increase. And so they have a plus, which is normally not mentioned, but reactants have a minus in front of the rate. All right? Yes. So this is how you can write them. Instantaneous rate. Consider a reaction. This instantaneous rate can be defined more like at a particular instant of time. What could be the possible rate of the reaction is how you can define instantaneous rate. Okay, the unit of rate is mole per liter per second. Very important. The factors influencing the rate of reaction: increase in concentration increases, increase in temperature increases, presence of catalyst increases. Why? Because catalyst helps in decreasing the activation energy. Okay? Then the rate law. Rate is equal to K into concentration to the power of A, B into B to the power of B. It is nothing but the law of mass action. But this is your rate law expression, where x and y are determined experimentally. You can see your x and y here, and may or may not be equal to a and b. But a and b here are nothing but the coefficients, if you can see here, right? They are the coefficients. But x and y are mostly determined experimentally. Okay, so x and y represent the order of reaction with respect to a and b. The rate constant. Larger the value of K, faster is the reaction. The value of K changes only with temperature for a given reaction, almost everywhere. So the unit of rate constant is this, and it changes with every order. Like first order has a different rate constant, like unit, second order different, zero order different. You just need to know this thing so you can apply it when if required. Order and molecularity. Consider general reaction. Molecularity is nothing but A plus B. In simple words, the number of reacting species is nothing but gives you the molecularity. Here you have A and B. So A plus B. For example, you have 3Na or 2OH here. So it will be 5. 3 plus 2 it will be 5. That's the molecularity. But order is X plus Y, and it might not always be equal to your coefficient, right? So molecularity is a theoretical concept. It cannot be zero, fractional, infinite, and imaginary. Orders at experimentally determined quantity, it can be equal to zero, positive, negative, and fractional. Can you see how it's contradicting? Now you have the pseudo order reactions. Okay, pseudo by itself means false. Okay, so in this reaction, concentration of water, one of the reactants, is in excess and its concentration remains constant throughout the reaction. So consider this reaction. Thus, the rate is directly proportional to this concentration. Therefore, the order is equal to 1. Okay. Now, the elementary and complex reaction. Reactions occurring only in one step are called elementary reaction. Reaction involving a sequence of elementary reactions are nothing but complex reaction. In case of a complex reaction, the slowest step is called the rate determining step. So, one more thing, when you see water, solvent, large, excess, any of that, think of pseudo first order reaction. These are the examples. Then you have the integrated equation. You can just go through it. Normally, there's, as I said, there's not many questions from chemical kinetics, maybe this year. But yes, then you have the half life period. This is of great importance because in the zero order and the second order, you have it to depend on the concentration, as you can see. But in the first order, it does not depend on the concentration. Important. Okay, and this is for the half life. First order tricks. So the T 75% is equal to 2 half lives, T 90% 2.303 half life, and T 99.9 is nothing but 10 half life. Just a thing that can maybe arrive in your paper. Graphical representation. This is something that you need to understand. It is important. You should know what increases, what decreases, how can the graph look like, or even like when they might give you 4 options and you need to determine the right option. So please go through this, the concentration time graph, rate concentration graph, and the half-life concentration graph for each of the orders, like zero order, first order, and the second order. Now you have the Arrhenius equation, important. K is equal to AE to the power minus EA divided by RT. Okay, so higher temperature, all that this Arrhenius has to say, equation has to say that higher the temperature, larger the K, and therefore faster the reaction. For every 10-degree rise in temperature, rate becomes double. And so a reaction with a higher value of A will have a smaller value of rate constant. Important. This is a graph that you could look at and just understand how this works. Okay, so higher EA, harder to cross the barrier. Smaller K, slower reaction. As I said, just one PYQ so far. So let's see what it has to say. The activation energy of a reaction represents the energy barrier that the reactant must overcome to transform into product. The difference between the energy of the product and that of the reactant. The difference between the kinetic energy and the potential energy of the reactant. The energy released during the progress of the reaction. The energy that is released only in the initial phase of any reaction in a solution. It's obviously A. Right? The energy barrier that the reactant must overcome to transform into product. And to reduce that energy is why you need a catalyst. And so it reduces the energy and quickly the reactants are getting converted into products. So that's for chemical kinetics. Now let's move on to periodic table. All right. So periodic table is more of a chapter with properties that you have to remember and understand, and it's how does it change when you go across a period, down the group, those kind of stuff. So let's start. These are the theories, are not important at all because there's no question so far, but let's just go through them. The Daubigny triads arranged elements in group of 3. Triads 3. So atomic mass of the middle element is average of atomic mass of the other 2 elements. Please note atomic mass. That's the highlight, right? So the drawback here is all known elements were not grouped into triads. And now you have the Lothamier's curve. Alkali metals occupy top positions in the graph, whereas the alkaline earth metals occupy descending positions, and therefore the halogen occupy ascending positions, right? Not important. And then you have the Newland's law of octaves. When elements are arranged in increasing order of their atomic mass, okay, then every 8th element starting from the first will have similar properties. The drawback is that valid up to calcium only, no position for inert gas, does not work for heavier elements. Mendeleev's periodic table. Periodic table, periodic properties of elements are periodic function of their atomic mass. Merritt's simplified study. Some vacant spaces was left for discovering new elements. Eka aluminium Ga or Eka silicon Ge corrected atomic mass of element. The drawback is that the position of hydrogen is not fixed and could not explain the cause of periodicity. To solve all of this, we have someone who came and gave the Moseley's law. Okay, so the periodic properties of elements are periodic functions of their atomic number. Up until now, it was atomic mass, but now we have the atomic number. What is periodicity? The repetition of similar properties of elements after a certain interval of time. And the cause of periodicity? The repetition of similar electronic configuration of elements after regular interval of time. This is just a quick IMAT rule. The position determines properties. Period, number of shells. Group, number of valence shells. And this is something that's important to crack any of the property questions that we're going to look on further. You need to know the three kings. I call them that. It's the effective nuclear charge, shielding, or distance. Very important. If you have the exam tomorrow and to break or crack this chapter, you just need to understand these three and you will be able to solve or approach every property in this chapter. The 18 groups and 7 periods, 4 blocks, S block, P block, D block, and F block, 4F series, lanthanoid series, 5F series, the actinoid series. Transition elements, elements which have incompletely filled d orbitals in the ground state or most common oxidation state. This is important. Zn, Cd, Hg are not transition elements. Very important. Pseudo transition elements, representative elements. Combined elements of S and P block are known as representative elements. Then you have the diagonal relationship. Li and Mg have similar charge by size ratio. And so is it with Be and aluminium. And then you have the nomenclature, not important, at least I haven't seen them so far. And then you have the effective nuclear charge. This is where we start the actual chapter. So screening effect S, which is greater than P, which is greater than D. And so F is the least. Trends along a period, the Z effective increases. Very important. Whereas along a group, Z effective almost remains the same, or rather, Z effective decreases. Okay, so more the positive charge, more is the Z effective. More the negative charge, less is the Z effective. Now you have ionization energy. Ionization energy can be defined as how difficult it is to steal an electron. Okay, so the energy required to remove an electron from an isolated gaseous atom. So ionization energy is always endothermic. And so because of that, delta H is positive. And yes, ionization energy of the first state is lesser than ionization energy of second, which is lesser than ionization energy of the third. Trends. Ionization energy is directly proportional to Z effective. Okay, so along a period, as we learned that because Z effective increases, ionization energy increases. Along a group, Z effective decreases, therefore ionization energy decreases. Yes, and now you have the atomic radius, the distance between the nucleus and the electron outermost shell. But it is impossible to find the exact value of atomic radius. And why is that? Because the atom is too small. Atom does not have a well defined boundary. Okay, so it's more of atomic radius can be defined more as it's a tug of war between the nuclear pull versus the electron distance. Okay, next you have the covalent radius, half of the internuclear distance between two atoms bounded by covalent bond. Then you have the metallic radius, half of the internuclear distance between two atoms by a metallic bond. Van der Waals radius, half of the internuclear distance between two nearest molecules in a non-bonded state. Van der Waals radius is defined for gases. Very important. Note, the van der Waals radius is greater than the metallic radius, which is greater than the covalent radius. Important. And then you have the trends. Along a period, Z effective increases, therefore atomic radius decreases. Along a group, Z effective decreases, atomic radius increases. Ionic radius. R cations is lesser than R of the neutral, and which is lesser than the R of anion radius. So radius of cation is the least always, and the radius of the anion is the greatest. Okay, so atomic radius is inversely proportional to Z effective. The Pauling scale and Millikan scale, not that important, you can just maybe go through them. Next you have electron gain enthalpy. Electron required or released when an electron is added to the outermost orbit of an isolated gaseous atom is known as electron gain enthalpy. Okay, in majority of the cases the delta EGH is negative, which is it's exothermic. It's mostly exothermic. Okay, except in Be, beryllium, the Be stable configuration or the noble gas is positive. Okay, the delta H is positive. So successive electron gain enthalpy is always and always positive. Now the trends again, it's directly proportional to Z effective. So along a period, the Z effective increases, therefore the delta EGH increases. And the same, along a group, Z effective decreases, therefore the delta EGH decreases. Next you have electronegativity. Tendency of an atom to attract shared pair of electrons towards itself. Okay, so electronegativity is directly proportional to Z effective. Along a period, Z effective increases, so electron negativity increases. Whereas along a group, Z effective decreases, therefore electron negativity decreases. This is the entire periodic table. This is important. So fluorine is more electronegative than oxygen, which is more electronegative than nitrogen, whereas nitrogen is almost equal to the electronegativity of chlorine. Okay? And then you have the inert pair effect due to poor screening effect of D and F orbitals. So the Z effective increases, NS2 becomes inert, does not participate in the reaction. Down the group, NS2 pair becomes inert. So the stability of lower oxidation state increases as you go down the group, whereas the stability of the higher oxidation state decreases as you go down the group. Okay, so the D and F block contraction, a screening effect, whereas where the S is greater than P, which is greater than D, which is greater than F. Poor screening, Z effective increases, and therefore the size decreases. How to find group, period, and block? S block, group 1 and group 2. P block, group 13 to group 18. Whereas D block is group 3 to group 12. F block is your lanthanoid series and your actinoid series. The nature of oxide: acidic oxide, basic oxide, amphoteric, and neutral. Acidic oxide, non-metals, SO2, all of this comes under your acidic oxide. Metals, here you have the X part, it's X and O. The X part here is a metal, whereas the X part here is a non-metal. Basic oxide, metal, here you have the basic oxides, and then you have the amphoteric oxide. Amphoteric oxide acts both as a basic and as an acidic oxide. And so these are the examples. Neutral oxides. Okay, please remember water is a neutral oxide. Yes. Higher the percentage of oxygen, more is the acidic strength. This can come as a MCQ. Wherever the oxygen is greater, the acidic strength is also greater. Right? So here you can see that in this example, you have oxygen to be the highest here, 5, here it's 4, and here it's 3. And therefore, N2O5, in the order, it falls the first. The same with SO2 and SO3. 3, therefore, greater. Again here, O has 7, therefore, it has the highest acidic strength. Along a period, the non-metallic character increases. Therefore, acidic strength increases. Whereas along a group, the metallic character increases. Therefore, the basic strength increases. Okay. This is important. Noble gases prefer low energy stable arrangements. And so they are inert in nature. Yes, this is a quick memory box just to understand the properties. So if Z effective wins, the effective nuclear charge basically, that is, it increases, the shielding decreases. And so the radius decreases, the ionization energy increases, and the electronegativity increases. But it's just the opposite if distance wins. The shielding increases, the radius here increases, the ionization energy decreases, and the electronegativity decreases. Okay, let's now move on to the PYQs. Here we have two questions from the year 2025. So yes, the compound FeCO3 is, first you find the oxidation number of Fe. It's relatively simple, but in case if you don't know how to do it, this is how you do it. You find the oxidation number and you get Fe to be plus 2. And you know that Fe2 plus is ferrous, whereas Fe3 plus is ferric. And so you have option A to be the right answer. Next question, in the periodic table, the atomic radius increases going. It can be as simple as this, just a basic property. So the atomic radius increases, yeah, from right to left and from top to bottom. Just the application of the properties. The next question, 5 atoms are shown below. The letters are not chemical symbols. Which one of the following atoms has the highest first ionization energy? Ignore mass number, only atomic number matters. Okay, so the ionization energy across a period increases, whereas up a group also it increases. Okay, so the full shell, very hard to remove an electron, right? So you can directly choose option B. Why? Because this is literally an inert gas, and therefore you can see that across a period the ionization increases. And so this is your answer. Option B. Okay. Next question. Which of the following substances has the weakest overall intermolecular force? Okay, weakest. Just a quick tip. When you have hydrogen joining with oxygen, fluorine, or nitrogen, it is hydrogen bonding, right? So it's definitely not any of, because it's hydrogen bonding, and hydrogen bonding is the strongest. So here you have to just compare, the only two options left is CO2 and CH4. But you need to compare size now. So CO2 has a stronger London force, and so it is smallest plus non-polar, and so it has the weakest intermolecular force. Therefore, CH4 is the option. Yeah. So for these kind of intermolecular force questions, remember this concept. Hydrogen bonding is the greatest, it's the strongest. And then you have the dipole-dipole, and then you have the London forces. Okay? The next question, element Z reacts with water at room temperature and hydrogen gas is released. The oxide of element Z is a solid at room temperature and does not conduct electricity. The oxide reacts with acids and has the formula ZO. To which group or part of the periodic table does element Z belong? Okay, so you have the oxide to be ZO. Oxygen, as we know, has a charge of -2. So Z would be +2 to balance it out, right? So you have -2 +2. It gets balanced. And so you have ZO. Group 2 elements form +2 ions. Oxide formula shortcut, just giving you a hint, G1, group 1, M2O, right? And G2MO, G3, M2O3. It balances out, it is a group 2 element, right? If you understand this concept, you can solve this question. Yes. Yeah. The last slide for this chapter. Which statement about a positive ion explains why it is positively charged? Okay, so positive ion is nothing but a cation. It has lost electrons. It has more protons than electrons. Okay, it's a theoretical question. So, positive ion, it has lost electrons, so therefore it has more protons. Yes, option C. The ion has more protons than electrons. Again, a quick shortcut. When protons is greater than electrons, positive ion. Electron is greater than proton, negative ion. Proton is equal to electron, it's a neutral ion. The last question, which of the following species have the same number and arrangement of electrons in their lowest energy state? Okay, again, I hope this reminds you of what we did previously. Positive charge, you subtract electrons. Negative charge, you add electrons. That's exactly what you are doing here. The charge is mentioned, you have to go according to that. So you know that K, potassium, has atomic number of 19 plus, so minus 1, and you get 18. That's how you go about each of that. And you get to know that Na and O2 minus have the same number of electrons, and therefore 2 and 4, right? Yes, so Na2 and 8 2 minus. Therefore, C is your option. I hope you understood. Let's now move on to the next chapter. Now we have chemical bonding, a force that acts between two or more atoms to hold them together as a stable molecule is known as a chemical bond. The reason is to attain stability to follow octet rule. Stability is inversely proportional to energy. Important. You have ionic bond, or also known as electrovalent bond, the electrostatic attraction between a cation and anion. Basically, a bond between a metal and a non-metal is an ionic bond. Electrovalency, charge on cation or anion in ionic bond. The favorable conditions for ionic bonding: low ionization energy of metal, high electron gain enthalpy. C is the high lattice energy, which is nothing but the force of attraction. The characteristics of ionic compounds: basically, they are hard crystalline solid. The salt, your NaCl, it's hard crystalline solid. High melting and boiling point. Highly soluble in polar solvent. Next, you have lattice energy. Amount of energy released when 1 mole of crystal lattice is formed. The lattice energy depends on charge and the size of atoms. Okay, so charge is directly proportional to lattice energy, whereas the size of atoms is inversely proportional to lattice energy. And then you have the Born-Haber cycle. It deals with the energy changes involved in formation of 1 mole of ionic crystal. Okay, and then you have covalent bond, very important. It is formed by the mutual sharing of electrons between combining atom. Bond pair, the pair of electron participating in bonding, whereas lone pair, the pair of electron not participating in bonding. Covalency is the number of bonds formed by an atom in a covalent bond. Here you can see in NH3 the covalency is 3 because there are 3 bonds formed. Here it's 5 PCl5, and so the covalency is 5. Coordinate bond. It's a special type of covalent bond in which both the electrons are given by one atom and accepted by the other. Basically, one atom both it donates as well as accepts electron, right? And then you have variable covalency. The number of bonds is equal to the number of unpaired electrons. Only valence electron participate in bonding. The drawbacks of octet rule is electron deficient molecule, hypovalent, or the expansion of octet, hypervalent, and the odd electron species. This is important, okay? The bond parameters: bond order, bond length, bond energy, and bond angle. Okay, bond order: the number of bonds between two combining atoms. H2, right? H2, you have one bond. CC, one bond. CC, you have two bonds here. So the bond order is 2. And then you have bond length, the distance between the nucleus of the two atoms. Bond length is directly proportional to the size of atoms, whereas it is inversely proportional to the number of bonds. Greater the number of bonds, lesser is the bond length. Yes, so you can see here, single bond is greater than double bond, which is greater than a triple bond. Bond energy, the energy required to dissociate any bond. So bond energy is directly proportional to the number of bonds, whereas inversely proportional to the size of atom. Very important. Okay, you can see that bond energy for single bond is lesser than for double bond, which is again lesser than for triple bond. Bond angle, hybridization, angle between two adjacent bonds, the VBT or the valence bond theory. Stronger the covalent bond, more is the bond energy and less is the bond length. Overlapping. Positive overlapping, same sign, lobes overlap, bond is formed. You can see here it's positive, positive. And so it is a positive overlapping. Negative, negative, same sign, positive overlapping. Negative, the opposite, you have different signs overlapping. Zero overlapping, effective overlapping is zero. So no bond formation. Alright? Yes. And then you have axial overlapping or end to end overlapping. Overlapping along internuclear axis, sigma bond is formed. S orbital always undergoes axial overlapping. Okay, and more close is the overlapping orbital to nucleus, more extent of overlapping and stronger is the bond. More the directional nature of overlapping orbitals, more is the extent of overlapping. Parallel overlapping or side by side or lateral overlapping or sideways overlapping. It occurs above and below the internuclear axis. Pi bond is formed. First bond is always sigma. The difference between sigma and pi, this is important. Sigma bond formed by axial overlapping, whereas pi is parallel overlapping. Stronger because the extent of overlapping is more in sigma bond, whereas here weaker because it is less. Allowed overlapping SS, SP, or PP. Here allowed overlapping of PP, PD, and DD, right? And free rotational possible in sigma bond. Here free rotation is not possible in pi bond. Okay, this is very important. You should understand that a single bond you have one sigma bond. In a double bond, you have one sigma and one pi bond. Whereas in a triple bond, you will have one sigma and two pi bond. Okay? And then you have the bond angle. Angle between two bonds. The order of repulsion is lone pair is greater than lone pair, which is greater than bond pair, bond pair. Okay? The factors affecting bond angle. Firstly, the lone pair. Secondly, the electronegativity of the central atom. And last, the size of the side atom. Lone pair is inversely proportional to the bond angle, whereas the electronegativity is directly proportional to the bond angle. The size of the side atom is again directly proportional to the bond angle. I know it's a lot of theory, but it is important because there might be two or three theory questions in the same options. So, unfortunately, you should understand all of this. And then you have the hybridization. Okay, overlapping of hybrid orbitals. Hybrid orbitals are identical in size, shape, and energy. Okay, all type of orbitals, that is empty, half filled, or fully filled, orbitals take part in hybridization. Hybrid orbitals orient themselves in space such that repulsion between them is minimum. So the order of repulsion is lone pair is greater than lone pair, which is greater than bond pair, bond pair. How to calculate hybridization? With the steric number formula. Here V is nothing but the number of valence electron, M is nothing but the number of monovalent atom, and C cationic charge, A an ionic charge. What is steric number? It's basically the number of bond pair and the number of lone pair. It's the summation of these two. Pi bonds play no role in hybridization, whereas number of sigma bond is equal to the number of surrounding atom. How to find a central atom? Least electronegative atom is the first property that you can choose while finding the central atom. Secondly, the hydrogen can never be a central atom. Very important. Polar molecule, the magnetic moment net is never equal to 0, and non-polar molecule, magnetic moment net is equal to 0. This small table here is important because it tells you on the hybridization. sp is linear, sp2 trigonal planar, sp3 tetrahedral, sp3d trigonal bipyramidal, sp3d2 is octahedral. These examples are important. You can just go through them. So in questions, you can choose the right option. Geometry includes lone pair. Shape ignores lone pair. Okay, so the geometry here, it includes the lone pair, and that is why you can see a difference here in between these two, between the geometry and shape. So this includes lone pair, but this does not include the lone pair. Yes. As it mentioned, NH3 geometry is tetrahedral, whereas the shape is pyramidal. So it's important for you to know both the geometry and the shape. Yes, and then you have the dipole moment. It's a vector quantity, you will know from physics. So it's equal to the Q into D. That's the charge into the distance. So more the electronegativity, more is the dipole moment. And here you can see the dipole moment of NH3 is greater than NF3. The application of dipole moment determine whether a molecule is polar or non-polar. To find the percentage of the ionic character in a covalent bond, or percentage of ionic character is equal to the experimental dipole moment divided by the theoretical dipole moment into 100, right? Symmetrical molecule, your dipole moment is equal to 0, whereas unsymmetrical, it is not equal to 0. And you can also apply the polar non-polar application here. Fajan's rule, not many questions asked, but covalent character is directly proportional to polarization. So, what are the factors affecting polarization? Size. For max covalent character, cation size should be small, whereas anion size should be large. Next, you have charge. For max covalent character, charge on cation and anion should be more. Electronic configuration of cation having pseudo noble gas configuration has more covalent character. Important. Drawbacks of VBT. Not very important, you can just go through the theory points. The main points of MOT. In atoms, electrons are present in atomic orbitals, whereas in molecules, electrons are present in molecular orbitals. Number of molecular orbitals is equal to number of atomic orbitals combined. When two atomic orbitals combined, two molecular orbitals are formed. So you have bonding molecular orbital and anti-bonding molecular orbital. You should know that bonding molecular orbital lower energy and therefore it is more stable, whereas anti-bonding molecular orbital higher energy, therefore unstable. Molecular orbital is under the influence of two or more than two nuclei. Electrons are filled according to the Aufbau principle, Hund's rule, and the Pauli exclusion principle. I hope you remember them. The molecular orbital are formed by linear combination of atomic orbitals, right? Here you have constructive interference, here you have destructive interference. Yes, bonding molecular orbital formed by constructive interference, lower energy and more stability. Increases the electron density in region between two nuclei, may or may not have a node. And then you have anti-bonding molecular orbital, again destructive interference, just the contrast of BMO. Higher energy, lesser stability. Electron density decreases between two nuclei. Formal charge, it is the subtract the valence electron minus half of the bonding electron. The types of molecular orbital, you have the sigma molecular orbital formed by overlapping along the internuclear axis, whereas the pi molecular orbital overlapping is done above and below the internuclear axis. And this you can probably look at it when the bond order is equal to half of NB minus Na. This is for BMO and the ABMO, right? So when the bond order is greater than 0, molecule exists, but when the bond order is less than 0, the molecule does not exist. Then you have the stability of molecule. More the bond order, more is the stability. If the bond order is same, then lower number of electrons in ABMO, higher is the stability. Bond order is directly proportional to bond energy and it is inversely proportional to bond length. Very important. Then you have diamagnetic, which has 0 unpaired electrons, paramagnetic at least 1 unpaired electron. This is a trick that you can use to solve these kind of questions. So what happens is that the bond order increases, okay, up to 14 electrons, you can see that, but right after that it starts decreasing, okay, but there's one exception, that is CO plus. Let us now solve the PYQs of this chapter. Yes, a pure covalent bond is a bond that forms between pure covalent, and therefore it can strike like examples like these, right? So therefore it's two atoms of the same element. Option A is the right answer. What kind of solid is NaCl? Textbook. question. So Na is a metal, Cl is a non-metal, therefore it is an ionic solid. Next question, why does hydrogen iodide have a higher boiling point than hydrogen bromide? Let's look at the options. The iodide ions in Hi are larger than the bromide ions in HBr. No. The Hi covalent bond is stronger than the HBr covalent bond. No. There are hydrogen bonds between Hi but not between HBr. No, it's not between both. The permanent dipole forces between Hi molecules are stronger than those between HBr molecules. No. The induced dipole dispersion forces between Hi molecules are stronger than those between HBr molecules. Yes. Why? Because Hi has a larger molar mass and larger electron cloud compared to HBr, and therefore it's more polarizable, stronger London dispersion forces, and therefore higher boiling point. And so you have option E to be the right answer. Okay, which of the following substance has the weakest overall intermolecular force? Weakest. We did it previously, if you remember. It would be CH4. Option B is the right answer. Which row correctly shows the shape of each molecule and whether the molecule is polar or non-polar? This is something that you need to decode separately. You should be knowing this to crack this question. Like, you should know the geometry, you should know the shape, you should know the hybridization. There will be questions based on that. So once you know that BF3 is non-polar and not polar. You know that this molecule is polar and not non-polar. CO2 is non-polar and not polar. NH3 is pyramidal and not trigonal planar, and therefore option 5 is the answer. PCl5 correctly matches. So row 5. Next and the last slide of this unit, which of the following molecules have an overall permanent dipole moment? CO2 is linear, symmetrical, and therefore non-polar. H2O bent, polar. NH3 pyramidal, polar. Symmetry cancels dipole. Okay, therefore bent or pyramidal usually is polar, right? So which of the following molecules have an overall permanent dipole moment? It is mostly 2 and 3. Option D, because they are polar. Okay, which option correctly describes the following features of a silane, that is silicon tetrahydride molecule? Number of bonding pair of electron, number of lone pair or non-bonding pair in the valence shell of the silicon atom bond angle. Again, as I mentioned, you need to know the hybridization, shape, geometry, all of that. And so once you crack that, this is similar to CH4 if you know, right? And so hybridization is sp3, shape tetrahedral, bond angle is 109.5 degree. So lone pair is 0. 4, yeah, option C is the right answer. Unfortunately, you will have to learn the table and try and crack this question. Alright, so now let's move on to our organic chemistry. We now have isomerism, which is part of our organic chemistry, obviously. So, in organic chemistry, the most important questions can come from isomerism and nomenclature mostly, right? So, let's start. So, what is isomerism? Anything that has the same molecular formula but different physical and chemical properties. Okay, there are different types of isomerism. Firstly, functional isomerism. By the word itself, it has different functional groups. And here are the examples. Alcohol and ether are functional isomers of each other, right? So you can see these two examples here. Here you have an alcohol, here you have an ether. And then you have aldehyde and ketone. Again, here you have an aldehyde and ketone, and so they are functional isomers of each other. And then you have acid and ester, right? Here you can see your carboxylic acid, and here is your ester. Functional isomers again. Cyanides and isocyanides. This is a cyanide, and this is an isocyanide. And amines, here you have your primary amine, secondary amine, tertiary amine. Next you have diene and ine. Ene, double bond. Ine, triple bond. Alcohol and phenol. This is the alcohol, but anything that's direct OH group directly attached to the benzene ring gives you phenol. The next type of isomerism is chain isomerism. The number of carbon atoms in the main chain is different. So carbon root is different. Okay, so your meth, eth, prop, that differs. So that's what they mean by carbon root is different. This is a quick checklist that you have to go through that can help in revising quicker. Next type of isomerism is metamerism. So the different alkyl groups on either side of bridging functional group. You have two different kind of alkyl groups. Here it's a methyl, here you have 1, 2 and 3. Right? So this is a methyl and this is a propyl. That's what they mean by different alkyl groups on either side of the bridging functional group. Ring chain isomerism. You can see the ring here. And that is what they mean by ring chain isomerism. So you have propene and cyclopropane to be an example. The next type of isomerism is position isomerism. Same functional group, same main carbon chain, but different position of functional group or substituent. Alright, so it's just about the position of the functional group and the substituent. Tautomerism. When two functional isomers exist in dynamic equilibrium. Keto-enol tautomerism. Keto form, you have this, whereas enol form, you have this. And so they exist in dynamic equilibrium to each other. Again, a quick exam trick that can help you in spotting the isomers quickly. Right? Yes, this is for position isomers. The conditions for tautomerism is must have at least one alpha hydrogen. This is the base. Anywhere it should have one alpha hydrogen at least. Alright? So on sp3 hybridized carbon. sp3 is anything that has a single bond. This is sp3 hybridized. And so this is nothing but has one alpha hydrogen. So this, the one directly attached to the first single bond, is nothing but alpha hydrogen. If neighboring atom is sp2, must have alpha hydrogen of sp3 atom in conjugation. The percent of keto-enol generally in equilibrium, keto is majorly present, but in few conditions, enol is dominating. Geometrical isomerism. Minimum of 2 sp2 hybridized carbon atoms having different groups. You can see here. Right? And this is where you have cis and trans. Cis, you have the thing on the same side, but this is on trans is on a different side, opposite side. Right? So EZ system when all the four groups are different. And that is the EZ system. Again, a quick memory trick. The rules. So the step 1, see the atom directly attached. Higher the atomic number, higher is your priority. So I is greater than Br, Cl, FON, CNH. Step 2, if directly attached atom is same, check the next attached atoms. So first atom is C in both the cases, right? Next atom is Cl, H and H in this case. But in this it is H, H and H. So CH2, Cl gets higher priority. That's about the priority list. Step 3, arrange the attached atoms in descending atomic number. So you compare one by one. Example, this is the example that they have given. So CHO carbon attached to OOH and CH2OOH carbon attached to OH and H. Here. So CHO is greater than CH2OH. And your last step, multiple bonds are counted as duplicate or triplicate. Double bond attached twice, triple bond attached thrice. And this can be your example. And step 5, isotopes. So higher the atomic number, higher is the priority. this is important. This is a quick speed table that you could go through just to figure out what could be the possible isomers and what you need to check. And now we move on to the PYQs. The PYQs are rather direct but a little tricky if you do not know the basic concept, right? So let's go through. Which of the following pairs of molecules are structural isomers? Okay, so let's check one. You can see that this one here is cyclopentane. When you try to solve it, it is cyclopentane. But this one is pentene. And so these are structural isomers. Can you see their molecular formula? It's the same. But number two, you can see that it is literally the same, just that it is flipped, right? You start counting C from this side 1, 2, and 3. And on this side, it's 1, 2, and 3. It's literally the same, just that it's flipped. So the connectivity is the same, longest chain is the same, and so it cannot be a structural isomer. Okay, and in 3, you can see that one is with nitrile or cyanide type, and other has different functional arrangement. You can make out, right? Definitely. So, but it has same formula, and so it is a functional isomer, right? So 1 and 3 are structural isomers. And so we have option A to be the right answer. The next question. Which of the following pairs of structural formula represent structural isomers? Okay. The first one, CH3, CH2OH, and CH3OCH3. When you try to combine it and get the skeleton of it, you get C2H6O. And here it's again C2H6O. And so it's functional isomers. Can you see? So yes. The next one, CH3, 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 CH2, CH2, CH3, and this one, they are same compounds, but they are not isomers. Alright? When you try to look at it, you will understand that they are just the same compounds, but they are not isomers. And for isomers, they have to have either a different functional group, a different position, anything of that. But that's not in this case. And so it's not 2. In third, when you try to get the skeleton, you will get C3H6O2. And so different functional groups. Therefore, it is 1 and 3. And you have option D to be the right answer. So same name after correct numbering is equal to same compound, but not isomers. Alright, so this is very important, and that's exactly what we've had, the problem we had here, right? So 1 and 3 are the structural isomers. So option D is the right answer. Which of the following organic compounds are structural isomers of each other? Okay, so try to get the molecular formula. Cyclohexane is C6H10, methyl cyclopentane is C6H12, hexane is C6H14, hex1-ene is C6H12, and 3-methyl-pent-2-ene is C6H12. Okay, you have 2, 4, and 5 to be having the same molecular formula. So, and obviously 2, 4, and 5. Option E is the right answer. I hope you've understood. The next question. Which of the following compounds are structural isomers of hexanoic acid? First of all, hexanoic acid is C6H12O2. Okay, so any structure with this formula, that is hexanoic acid, can be its structural isomer. Alright, so here the first one, you have ester with 6C and 2O, right? And the second one is cyclohexane diol. And the third one is a double bond, and so it reduces, you have double bond here, and so it tries to reduce the 2 hydrogen. Therefore, you have option 1, 2, and 3 to be the right answer. Because yes, when you try to break down and get the molecular formula of this, you will see that it is the exact same molecular formula as hexanoic acid, right? And so you have option D, 1, 2, and 3 to be the right answer. This is the same question as before, so you can take it as practice. The next question and the last one, which of the following hydrocarbons are structural isomers of hexane? Now, hexane is C6H14, right? Again, get the condensed formula of this, and you have it to be C6H12. The second one is C6H14. The third one is C5H12, right? And so the only thing that matches this is obviously 2. So it's option number A. And this is a quick checklist. You can go through this. And with this, we're done with isomerism. Alright, we now move to IUPAC nomenclature. So here are some common names and let's start. So word root. We all know that we need to know the word root to go about the nomenclature first. So meth, eth, prop, bute, pent, hex, hept, oct, noc, and det for 1, 2, 3 and respectively. So what is the, how do you say, like a proper blueprint that you have to follow while doing the nomenclature is, first you have the secondary prefix, okay, and next you have the primary prefix, then you have the word root, then the suffix, and finally the suffix, okay. And here the suffix here is primary, and the suffix here is secondary, okay. And this secondary prefix is normally side chain or a substituent, whereas the primary prefix is cyclo, bicyclo, spiro, or anything of that. And suffix, which is secondary, is the functional group. Okay, and yes, the suffix which is primary is either alkane, alkene, or alkyne. The secondary prefix, we are now moving into the depth of it. The secondary prefix, which is either the substituent or the side chain, you have fluoro, chloro, bromo, iodo, nitro, alkyl, methyl, ethyl, propyl. Now, why is this secondary? Because you can see to this carbon atom, you have 2 carbons attached, and therefore this is secondary. Vinyl, you have a direct double bond attachment, and so it's sp2 hybridized here, right? But allyl, that's not the case. Here you have there is one double single bond, and after that it's not the one that's right next to it, but it is next to the carbon atom that is attached to the double bond, so it is sp3 hybridized, right? And here tertiary, again this carbon atom has 1, 2, and 3 carbons attached to, so it is tertiary nature. Neopentyl. Neopentyl is when you have 3 CH3 groups attached, right? Can you see 1, 2, and 3? So neo. Now, what are the rules that you need to follow to go about nomenclature? So first and foremost, you have to select the longest continuous carbon chain. So if the number of carbon atoms in the main chain is same, then select that chain which has more branches. Alright. The second is numbering. Very important. Numbering is done in such a way that the substituent gets the lowest number. Okay. So if first point of difference is same, check next point of difference. So if substituents getting same number, alphabetical order is preferred, like how we have in school, okay, the roll number wise. So if the last point is that if substituents getting same number, then alphabetical order is again preferred. This is the same thing. Alphabetical rule note, di, tri, tetra are not used in the alphabetical order. Very important. Okay. And now you have alkene and alkyne. Obviously, you know alkene is nothing but double bond. Alkyne is the triple bond. And they've just given you a name, the structure, and the name of it. You can see that here it is in alphabetical order. Now we have the functional group. Very, very important for nomenclature. So atoms or groups of atoms which decide the chemical properties of a molecule. So carboxylic acid, aldehyde, ketone, alcohol, cyanide, acid halide, amine. Very important. You have to know the suffix and you also have to know the prefix which is here. Yes. Okay. So the thing is, this is the priority list. So carboxylic acid holds the highest priority, and then you have aldehyde and respectively. So higher the priority, it is acts as the suffix. Okay, not the prefix but the suffix. So higher the priority, it has to be the suffix, and then you put the substituent and the other things respectively. So this is the prefix that you should also know, which is important. And if you have this in this list, if you have both in the structure, the higher one always goes behind as the prefix. Just remember that the one that comes after it is the prefix. Yes, that's the prefix, and the higher one goes as the suffix. Yes, these are the different positions of benzene. We know that ortho is at the 1 and 2 a position from the CH3, meta is at this position, and para is here, right? Just an important tip. So here, always prioritize functional group, and then you have the double bond, and then the triple bond, and then lastly, it's the substituent. And now we move on to your PYQs. So let's see how it goes. What is the correct IUPAC name of this compound? Okay, so you can see that OH is highest priority and so should be given the least number. You find the longest chain. Okay, so it's definitely starting with OH because of the priority order. So you start 1, 2, 3, 4, and 5. So at 2, you have OH. So which one as, okay, there are many, 3 options with OH at 2. Okay, and then you have 3 dichloro. Okay, so not this, dichloro. And let's move to 3 comma 3 dichloro, 4 dimethyl hexane to all. Yep, so it's option A, which is the right answer, right? So you have 4 dimethyl hexane to all. Option A is your right answer. The next question, what is the molecular formula of the compound shown below? Very easy. You have C6H10. If it's confusing, just try to break this down and try to separate it as a long chain, and you will be able to definitely answer. Okay. Next question. The structure of paracetamol is shown below. Okay, which one of the following functional groups is present in paracetamol? Can you observe? It's an amide and not amine. We know that this is an amide, right? And so it is amide. Option E. The next question, which one of the following molecules is a structural isomer of methyl cyclopentane? Okay, so we know that methyl cyclopentane is C6H12. So try and get the molecular formula for each of this, and you will automatically arrive at your answer. We get C to match C6H12. And so we have option C to be the answer. Next question. The formula of a molecule, the formula of a molecule is this. So which functional group is given below are present in the molecule? Okay, when you try and break down this formula, you will get CC, which is an alkene. Okay, and then CO, ketone, CHO, aldehyde. So alkene, ketone, aldehyde. 1, 3, and 4. Option A is your right answer. You just need to break down and give the bonds respectively. And once you know how to do that, these are super simple. The next question, how many unbranched straight chain molecules are there with the molecular formula this, but with a different structural formula? Okay, so this as C4, right? So try and write that down. And when you try and play, you just need to play around with these formulas. C1 can be equal to C4, and C2 can be connected with C3. And with that, you try and add 1:1 both F on carbon 1, right? Or at this carbon, you can add both the F, which is F2 here. The next possibility, 1F on C1 and 1 on C2. The next possibility, 1 and 3, 1F on C1 and another 1 on C3. The other possibility is 1F on each end, 1 and 4. That's here and here. The next possibility, 2 and 2, both F on carbon 2. The other possibility, 1F on C2 and 1 on C3. And so you have 6 possible isomers. This is tricky because I struggle finding the isomers. You just need to write it out. Unfortunately, you need to, as I said, you need to play around with these questions, because that's when you will arrive at the right answer. If not, unfortunately, it's going to be hard, So, yes, this is a way that you can use to solve your questions. The last question, a very easy one. What is the correct formula of propanal? Okay, so propanal, aldehyde. This is an alcohol. Not this, not this, not this. Can you see an aldehyde here? So, yes. So, option E is the right answer. You have 1, 2, and 3. So, prop. Yep. With this, we are done with nomenclature. Now we have GOC, a really theory-heavy chapter. Of course, for the IMAT, up till now, they haven't asked very difficult questions like we have in the PDF, like the theory that we have. Please just learn the basics and you are good to go. Here, bond breaking, heterolytic fission, and homolytic fission. Heterolytic fission is favored by polar bonds or the polar solvents. Important to know, and that's it. Homolytic fission, it's favored by light and peroxide or the non-polar bonds. Okay. Now you have electrophiles, electron-loving species. Okay, so they are electron deficient and so they want more of it. So Lewis acid or positively charged species. Right, here are your examples. And now you have nucleophiles. They are again nucleus loving species. And because this is a Lewis acid, this will be a Lewis base or an electron donor. And so it's negatively charged. Here it was positively charged. Here are your examples. Reaction intermediates. Species which are formed during reaction and are consumed by completion of the reaction. So we have carbocation and carboanion. Carbocation, and so positive charge on carbon atom. Alright, and here we have carbanion, and so it's negative charge on the carbon atom. So the properties here, it's electron rich, it's nucleophile, Lewis base, and diamagnetic. But here it is electron deficient, electrophile, 3 bond, and so 6 electrons, and diamagnetic. Okay, you know that 1 bond means 2 electrons, right? And therefore 3 bonds is 2 into 3, which is 6 electrons, in case if you're wondering why was that. Free radicals, odd electron species. And can you see the free radical here? And these are the types: allylic, vinylic, benzylic. Neutral species, electron deficient. Okay. And then you have the electronic effects, permanent and temporary. Under permanent, you have inductive, resonance, hyperconjugation. But under temporary, you have electromeric effect. Inductive effect is more like electron pulling or pushing through the sigma bonds. Okay, so again, displacement of the sigma electron along a saturated carbon chain. It operates through sigma bond. It depends on the distance and decreases with distance. So partial displacement of electrons. Okay, so you have minus I effect and plus I effect. Minus I are all the electron withdrawing group, and they are basically the high electronegative atoms. Okay, whereas the plus I effect is the electron donating groups, and this is your order. For electron donating groups is like your alkyls basically, right? Can you see the alkyls. So, yeah, the application of inductive effect, stability of carbocation, stability of carbanion, and the stability of free radical. Okay, so here, this is important. Stability of carbocation is directly proportional to electron donating group, and so that is the plus I group, all of this. Okay, whereas the stability of carb anion is directly proportional to the electron withdrawing group. Just look at the contrast, right? And lastly, the free radical stability depends on hyperconjugation and the inductive effect. Next, we have resonance. Okay, the delocalization of pi electrons. Okay, so highly resonating structures are not real, it's just imaginary. The resonance hybrid is what is real structure. The benzene that we have is also a resonance hybrid. Okay, so resonating structures are also called canonical structures. So resonating structures are hypothetical, and resonant hybrid is real and the most stable, and resonance is permanent. Important rules: opposite charges close, most stable. Okay, like charges closed, most unstable. More like your like charges repel and unlike charges attract. So, negative charges on more electronegative atom, more stable. Positive charge on less electronegative atom, again, more stable. And this is an example. The stability of resonating structures. More pi bonds, more stability. The neutral structures is greater than the charged structures. Complete octet structures are the most stable. Okay? And extended conjugation and cross conjugation. Extended conjugation is more stable than the cross conjugation. I know a lot of theory, but just try and understand the most important points. Otherwise, it's too much theory. I totally get it. Yes, and the conditions of resonance. You have empty orbital, lone pair, odd electron, pi bond, back bonding. Okay? So, yeah, resonance stabilizes molecule by delocalization of electron. More number of contributing structures, more the stability. Equivalent structure, maximum stabilization. The types of resonance: plus R, plus M effect, the electron donating group. And the example here is your phenol type. Effects: it increases the electron density on benzene. Electron density increases at ortho and para position. No effect on meta. Important. Okay, so no effect of distance. How do you identify plus R? It's basically the lone pair containing groups. Minus R, minus M effect, the electron withdrawing groups, just the opposite. It decreases the electron density on benzene. Electron density decreases at ortho and para, and no effect on meta, no effect on distance. The important part here is the application of the resonance effect. Please note that the stability of a carbocation or a free radical is directly proportional to the electron donating group, but inversely proportional to the electron withdrawing group. And the same thing here, it's directly proportional to plus R, whereas inversely proportional to minus R. Carboanion stability is directly proportional to electron withdrawing group, whereas inversely proportional to the electron donating group. Here again, stability is directly proportional to minus R, whereas inversely proportional to plus R. Heat of combustion. Heat of combustion depends on the number of carbon atoms, and the stability is inversely proportional to the heat of combustion. Maybe a theory question. Okay, aromaticity, the stability. How is aromatic compounds related to the stability? Aromatic is the greatest in stability, and so aromatic is more stable than non-aromatic, which is more stable than anti-aromatic. Here you can see also aromatic are cyclic in nature. They are planar, and so sp2. Resonance in the entire cycle, and very important, they follow the Huckel's rule. Okay, and what is Huckel's rule? Anything that follows this particular trend, 2 6 2 pi, 6 pi, 10 pi, when the n is 0 1 2 3 in this formula, they follow Huckel's rule, and so that time they are aromatic in nature. All right, but anti-aromatic, it's cyclic, planar, resonance in the entire cycle, but the condition is this: And so this is not similar to the Huckel's rule condition, right? But this is the condition that they follow. Hyperconjugation. It's also known as no bond resonance or the Baker-Nathan effect, right? And the definition is the overlap of sigma electron with adjacent pi bond or vacant orbital is called hyperconjugation. Very important. What is the condition for hyperconjugation? It should have at least one alpha hydrogen on the sp3 hybridized carbon atom. Okay? Hyperconjugating structures overlap of the sigma electron with adjacent bond or vacant orbital is called hyperconjugation. Now, heat of hydrogenation. HOH depends on the number of pi bonds, and so it's directly proportional to the number of pi bonds. Yes, and this is the stability order. Application of hyperconjugation. Stability of carbocation and free radical. All right, and you can look at it here. The types of hyperconjugation: plus H, which is nothing but electron donating group. The resonance of the hyperconjugation increases electron density. So the electron density increases on benzene. Electron density increases at ortho and para, no effect on meta. I think this is the third time that this comes up. Minus H, electron withdrawing group. The electron density decreases on benzene. Electron density decreases at ortho and para, again, no effect on meta. Order of effects: aromaticity, again, it holds the highest order. And then you have resonance, hyperconjugation, inductive effect. Effect of hybridization: Sp is always greater than sp2 and which is greater than sp3. Acidic character. Just remember this, its acidic strength is directly proportional to electron withdrawing group and it is inversely proportional to the electron donating group. Okay, and the ortho substitute benzoic acid are the strongest among isomers. And then we have the basic strength: more lone pair availability, more basic strength. Compounds in which lone pair is delocalized is less basic, whereas compounds in which lone pair is localized, it's more basic. And this is our classic NCRT example, where in gaseous phase, tertiary amines is greater than secondary amines, which is greater than primary, which is greater than NH3. Whereas in aqueous phase, it's a different condition. Secondary is greater than primary and then tertiary, and then you have NH3. This is when CH3, when the alkyl group is CH3. If the alkyl group is CH2 or C2H5, you have this to be the order. There's a switch here. Okay? Ortho effect. Ortho substituted anilines are weakest bases among isomers. And so the reason is steric inhibition of protonation. So basic strength is again directly proportional to electron donating group, whereas it's inversely proportional to the electron withdrawing group. Okay, so base is a OH donor, electron donor, and H plus acceptor. More the lone pair availability, more is the basic strength. Okay, so yeah, we move on to the PYQs. This is a 2025 PYQ, very simple. So in benzene, okay, the first option says all the carbon atoms are sp2 hybridized and the molecule has a planar structure. Isn't that correct? Because this is the structure of benzene and it is sp2 hybridized and it is indeed a planar structure. So option A is the right answer. Okay, which of the following statements are about amino acid is true? Again, a 2025 question. They contain an amine group and a carboxyl group. Amino acids contain an amine group and a carboxyl group, if you know how it is written. So option A is the correct answer. The next question, what is the molecular formula of the compound shown below? When you try and write the entire structure down, you will know that it is cyclohexene, and again because of the double bond. So one ring and one double bond, and you can use this formula to get your answer and you will get C6H10. Again, if you are confused on finding what could be the possible molecular formula, please try and break it down into the normal how we normally write it, and 100% you will be able to figure out what's the molecular formula. Okay, which of the following substances has the weakest intermolecular forces? Okay, we have done this question, right? I think in chemical bonding. But anyway, weakest intermolecular forces, but you can see H, F, and Ho, H and F, and N and H. This is hydrogen bonding, so strongest, so definitely just score that out. CH4 and CO2. This is stronger, has stronger dispersion than CH4 because it is larger, and so it's not CO2. CH4 has the weakest overall intermolecular force. Okay. Next question, which of the following functional groups is present in cysteine? Okay, here you can see this is a bit tricky because you can easily get confused by OH and directly mark alcohol. But do you see something weird here? It's thiol, right? And when you write the entire structure down with the C and H, you will see that it's actually a carboxyl group. Okay, it's a carboxyl group and it's not OH. So as soon as you see OH, don't blindly mark, okay, alcohol done. No, that's not how it works. Try and write the entire formula down. You will get it has carboxyl group, and this is thiol, which is attached to CH2 here. So thiol is your right answer. Next question, the formula of a molecule. This, which functional group is given below are present in the molecule? Okay, we did this earlier, right? In the previous chapter. So again, when you try to break it down, write all the structures, you will get alkene, aldehyde, and ketone. Last question of this chapter, which of the following separation technique can be used to obtain liquid ethanol from an aqueous mixture of ethanol, ethanol, and ethanoic acid? Okay, so because it is three different functional groups, right? You have three different functional group. It can be possible through fractional distillation, not centrifugation, not filtration. Okay, miscible liquids with different boiling points is fractional distillation, and insoluble solid plus liquid is filtration. Suspension is centrifugation. Okay, and so you have option 2, that is E, to be the right answer. With this, we are done with GOC. We now have the last and final chapter of this long lecture, hydrocarbons. So let's crack it together. We have alkanes. Okay, there's a lot of reactions, and it's everything that's in your NCRT is here. So it's condensed. So it's something that you have to go through by yourself and understand the tricks that we have provided here. Okay, so it's easy for you to understand. All right, so alkanes, these are the set of reactions that alkanes has. There are about 14. Yeah, you will have to go through it here by yourself. So hydrogenation is pi bond breaks and H adds. From alkyl halides, X removed, H added. Wirtz reaction, the main reactants and the catalysts. So please do learn all of this too. Alkyl halides couple. Decarboxylation, NaOH and CaO, which is nothing but soda lime. And then you have CH4 to be formed. Kolb's electrolysis, same as Wirtz reaction, even carbon alkane forms. Franklin reaction, your alkyl halides couple. Corey-House synthesis, Gilman's reagent is this, and so this is the entire reaction. Halogenation, H replaced by X. Aromatization, alkane or cycloalkene, and you get an aromatic compound by the term itself. Isomerization, straight chain alkane, you get a branched alkane. Combustion and controlled oxidation, reaction with steam, pyrolysis. Please try and go through the skeleton so you could at least figure out what could be the possible reaction. But learning the reagents, learning the catalyst is important. It's important for you to know at least which reaction has which catalyst. Next, you have alkenes. You have hydrogenation of alkynes, Birch reduction, dehalogenation, dehydration of alcohol, which is important, dehydrohalogenation, and halogenation. Your interhalogen, X2 in polar solvent, addition of HX, addition of water, hydroboration oxidation, oxymercuration demercuration, addition of HBr or peroxide. Okay, here you have reductive ozonolysis, and you have oxidative ozonolysis, and yep, that is that. And here you have chlorination, bromination, and the special reagents. Lastly, alkynes. From carbides, from dehydrohalogenation, the test for unsaturation, this is important. Okay, then you have Kucherov reaction, hydrohalogenation, and the coupling reaction. Yes, and linear cyclic oxidative. Please learn the silver nitrate test is a white precipitate. Cuprous chloride test red. Bayer's reagent, you have this to be happening, and this is your ozonolysis. So oxidation and reduction happening here. The next one is the lower to higher alkyne, Leucid formation, internal to terminal alkyne, terminal to internal alkyne. Aromatic hydrocarbons. Okay, so method of preparation of benzene, coupling, cyclic coupling of alkyne from phenol. I think this is a classic one. That's a super easy one. And the last one is decarboxylation. Okay. Properties of benzene. Electrophilic substitution reaction. So firstly, nitration. Okay, this is your mechanism. Halogenation. The intermediate here is halonium ion. Friedel-Crafts alkylation. And here you use Al anhydrous AlCl3. Friedel-Crafts acylation. Here you use again anhydrous AlCl3. Here rearrangement is possible, but in this case it is not possible. Okay, sulfonation. Here you have concentrated H2SO4 and oleum. This can be a question on basic, like what is oleum, choose the right option, and they will twist you with changing the subscripts of this. So it's important for you to know what is oleum. And yes, this is the generation of electrophile, and it is just combined and given as a single box. Mechanism of electrophilic substitution, the formation, first step, formation of carbocation, which is a sigma complex or a valent intermediate. Removal of proton is your second step. Then the direct influence of groups, okay? Plus M or plus R, electron donating. Direct substitution to ortho and para position. Minus M and minus R are electron withdrawing. So the direct substitution to meta position. The reactivity order is plus M, that is electron donating group, is greater than minus M, which is electron withdrawing group. Addition reaction, benzene, so chlorination, excess in the presence of UV, right? Also called Lindane or Gamexane reaction. Hydrogenation, the condition here is high temperature and high pressure. This can be tested. They can twist this by saying low pressure or whatever. And the catalyst here is nickel. Oxidation, the condition here is odd alkaline KMNO4. The product is benzoic acid for oxidation of benzene. Finally, we come to our PYQs. Let's see what this chapter has to offer. Which one of the following substance has the highest solubility in the specified liquid at a temperature of 298 Kelvin and 1 atm pressure? Okay, this is something that we did, right? I think in solutions, I don't know, but we did this question. Simple. So sodium chloride in liquid cyclohexane. Sodium chloride is ionic. Cyclohexane, no. So definitely not option 1. Option 2, bromine in liquid hexane. Bromine is nonpolar and liquid hexane is nonpolar, and so This follows like dissolves like, non-polar dissolves non-polar, and polar dissolves polar. A 2025 question. Glycogen. Okay, this comes from biomolecules, which you will learn in biology. So it's important for you to learn these the components and the structures of what it is formed of and all of that. So it is tested here. So glycogen is a homopolysaccharide, heteropolysaccharide, disaccharide, a storage molecule present in both animals and plant cells. No, is a polypeptide. It's a homopolysaccharide. Why? Because it's made only from glucose units. Okay, what is the molecular formula of the compound shown below? We did this one too, if you remember, like I think the previous chapter. So cycloalkene, right? And so it's when you put it in the formula, C6H10. Option 1. Which one of the following statements correctly describes the type of mixture and the most appropriate method used to separate the specified component from the mixture? Okay, for this, yes, I have made this memory box that you can go through. This has all the methods used and what is the situation. Okay, and this is the key ideas that you can go through. Okay, this is actually very important. Please find time to go through them and understand this. You have questions based on the same. All right, and so salt from salt solution, homogeneous, paper filtration. No, definitely no. Water from salt solution, heterogeneous, simple distillation. Heterogeneous? No. And chlorophyll from a solution of different plant pigments. Homogeneous, whereas it's chromatography. You see pigments, you see chromatography, it has to strike your mind. And it is homogeneous. Chlorophyll from a solution of different, yes, it is. And so, therefore, third is the right answer. Red blood cells from blood, homogeneous centrifuge. No, it's not homogeneous though. Gasoline petrol from crude oil, heterogeneous simple distillation. When you see crude oil anywhere, it's from fractional distillation only, and it's only possible through that. And so, to understand this, I highly recommend you go through this and understand this for you to solve that or any kind of questions that can occur. Okay, so now we have the last and the final question of the entire lecture. So, I hope please give it your best for the last one. So yes, the question says consider the following general equation that describes one way of synthesizing a particular type of biofuel represented as Y. Okay, so X represents a neutral, uncharged organic molecule involved in the reaction. Which of the following statements about the reaction are correct? Okay, so once you see, try and examine the entire reaction. This does remind you of something. Isn't this a glycerol, right? Can you see this? Isn't it a glycerol? Yes, it is, right? So, once you know this is glycerol, can you look at this side? Yes, this is a triglyceride, right? But the only difference is it is on the opposite side of what we already know from esterification. And so it is basically transesterification, the reverse of esterification. And so this is a biodiesel formed. So biodiesel is, as it's mentioned here, is or biofuel is basically a fatty acid, and it is methyl or ethyl ester. Biofuel from oils is transesterification. Therefore, triglyceride plus alcohol, which is your 3x here, gives biodiesel ester, and glycerol. Okay, so the product is an ester and the small reactant is alcohol. Let's move to the options. The addition of an enzyme is an essential condition. No, it's never an essential condition. No. Y is an ester. Y ester? Yes, Y is an ester. X contains an alcohol group. Yes. And therefore, 2 and 3 are the right options. And so this is why you need to know the skeleton of all of this from the previous equations that we did. You might have these kind of questions, and it's important for you to catch the trick anywhere look at. All right, with this we are done, and I hope it was helpful, and I hope you gained at least something out of this. Thank you so much for staying along, and I wish you luck and all the very best for the IMAT exam.